Students, I hope that you are doing well now. We started Unit 6 last time, and I'll take you to where we stopped last time. We were discussing Ampere's law. It tells you about the magnetic field strength of a current carrying wire, and we call it circulation sum. Let's discuss it a little bit. So, if you have a current carrying wire, what Ampere says is like that. It has to be a straight, infinitely long wire. As current flows in one direction, let's say, a constant current, how strong is the magnetic field at some given distance here? To find that, Ampere said, at that particular point, you determine B and dot it with a small distance element, B dot delta S, as it shows here, S or delta L, length element, you can see here. So, let's say I'm here. How strong is the magnetic field? Magnetic field strength at this point, dot a small distance or displacement element, plus, again, B dot. It could be another B, not necessarily the same B. B dot delta L plus. You keep on doing like that, and you go around the wire. And he said, the sum of B dot delta L is equal to the sum of a constant mu0 times the sum of currents in the distance or in the path along which you travel. So in that circumference area, as you can see from here. So if you have only a single wire, then and there is only a single current, you have mu0 times R. Not since actually, if you are wise enough and you keep the same distance from the wire, you argue that the B at this point and the B at the next point will not be different in magnitude, not in direction, in magnitude. So B times, you get delta L times cos 0 degree, because magnetic field strength, direction and displacement are in the same direction. Right hand rule of magnetic field strength, do you remember? The magnetic right hand rule of a single current carrying wire. So you get cos 0 degree. Cos 0 degree is 1, so you have the sum of it. Since B is constant, B will be factored out. I said B is constant if you are at the same distance from the wire in all directions, meaning you are moving along a circle. So you have B times the sum of delta L. So if you travel along a circle, the sum of delta L will give you circumference. As you know, circumference is beta 2 pi r, so you get B times 2 pi r is equal to mu0 times r. There you are. If you can measure the current, and this is constant to permeability, constant, and since the distance you can easily determine, B of a current carrying wire is known. Therefore, B equals mu0 times I divided by 2 pi r. That's all. That's what this problem discusses. Let's go back to this problem and see if you can solve it easily. Homework 21. It says, determine the magnetic field strength at a distance of 5 centimeters from a current CC means current carrying, from a current carrying wire of current equals 2.4 amperes. So, you say, solution, and the distance is equal to 5 centimeters from the wire. The current is 2.4 amperes. Permeability is given somewhere. As you can see, it's also given here. It's a constant. So the required quantity is how much is the magnetic field strength of the current carrying wire at a distance of 5 centimeters. Perpendicular distance, by the way. At the distance of 5 centimeters from the wire. So the formula, since it's something that we determine experimentally, you have to study it by heart. You say this implies B is equal to mu 0 I over 2 pi r. Substituting, you get 4 pi times 10 to the power of minus 7. It's in SI units, Tesla, meter per ampere, times the current is 2.4 ampere divided by 2 pi r, 5 centimeters. 2 pi times 5 centimeters means you have studied prefixes by heart, so you get 10 to the power of minus 2 ampere, meter. So you can see here, meter in the numerator, meter in the denominator will cancel out. Ampere here at the top and ampere here under the dividing line. The two also cancel. There remains only T, Tesla. So 2 pi cancels 4 pi to get 2. It's a very simple problem now. You have 2 times 2.4, this one, times 10 to the power of minus 7, divided by, remember, by 2 pi we cancel 4 pi, we got 2 here, and I have 5 times 10 to the power of minus 2. And the unit, Tesla. So how much is this? It's not a big deal. If I were you, I would solve it. There are many ways of solving the problem, but find a mathematically simple method. 10 to the power of minus 2, cancel 10 to the power of minus 7, and get 10 to the power of minus 5. Instead of cancelling by 5, I have an easier method. Multiply by 2 here. When you multiply by 2 here, you get 10. Multiply by 2 here too. Numerator and denominator by 2. 2 over 2. So 2 times 5 gives you 10. When 10 comes to the numerator, it becomes 10 to the power of minus 1. With 10 to the power of minus 5, it gives you 10 to the power of minus 6. So we have like this. Times 10 to the power of minus 6 Tesla. How about the numbers? So 2 times 2, 4. 4 times 2.4. 4 times 4 is 16. 1 would be carried over to the left. 4 times 2 is 8. 8 plus 1 gives you 9.6. So 9.6 times 10 to the power of minus 6 Tesla. Either you can call it like that, or you can use a prefix and call it 9.6 micro Tesla. That's it. Now let's go over to another topic here, in which we apply Ampere's law. By the way, since you're going around the wire, it's called Ampere's circulation sum. You find the name here. The summation is called circulation sum. So the next topic that we have to pick is an application of Ampere's law, and we want to know how much is the magnetic field inside. Let's come over here. Inside a thick wire like this, as you see in the drawing. And so to find the magnetic field strength, we apply Ampere's law. We say B equals mu 0 I over 2 pi r. But the problem is now, we have a thick wire. You're, let's say, somewhere inside the wire at some distance r, as you can see here. And the radius of the wire is something different. In that case, what will you use for I and what would you do for r, and how do you get B? There's another formula which you have to apply. Experiment shows that when current flows through a thick wire like this, the current density is the same everywhere at whatever distance you are from the center of the wire. JR equals JR. This is very important, that the current density at some smaller distance than the radius of the wire and out to the end of the wire, meaning capital letter R, radius of the wire, the current density is the same. And I hope that you remember current density means current divided by cross-sectional area. When you apply or use the two formulae, then you can get the magnetic field strength inside the wire at any distance from the center of the wire. Here it's a bit difficult to show you where you measure distance from, but you can see distance will be measured from the center of the wire outward. Up to here is the radius, and anywhere less than that you have small letter r. So, how much is the magnetic field strength? This I is the whole current inside. But if you want to find out the magnetic field strength up to some distance r, this must change. I is wrong. You have to write down the corresponding current. So write down IR. What does IR mean? The current within the radius of small letter r. So at any distance, how much is that? We carry on with this thing here. JR means current divided by area. And inside the circle, cross-sectional area, as you know, is pi r squared. So we have I over pi r squared. And this one here too is IR. Remember, the difference between this IR and this one is, this is only a small portion of the current, this is the total current, divided by, again, the small cross-sectional area, pi r squared. So when you equate the two, you see, pi cancels pi, and therefore you get the small current IR within a smaller distance of small letter r is equal to I times pi r squared divided by pi r squared. Now you can see pi and pi cancel out, so we get the total current I times r squared divided by r squared. That gives you the current within some specified distance. So if you want to find the magnetic field, then we apply Ampere's law. B, therefore, equals mu 0 IR over 2 pi r. You can get I, but it's difficult to get IR. So how do you get IR? From this simple formula that JR, the current density within any specified volume, is constant. Therefore, IR we get here and substitute it in here. So I get B equals the magnetic field strength at any given distance inside the wire is equal to mu 0 over 2 pi r times IR. And IR is I times r squared over r squared, small letter r squared. Now you can see then this small letter r cancels one of the r's over here. And at any distance then, B equals mu 0 R, the current, the total current is a constant. What can change is only your distance from the center of the wire divided by 2 pi r squared. So the formula is actually simple, but you have to remember two things. That the current density is constant and Ampere's circulation law. So let's look at homework 22. It says, find the magnetic field strength inside a current carrying conductor of radius 4 millimeters at a distance of 3.6 millimeters from the center of the conductor when it carries a current of 2 amperes. You see, this is very, very simple. An application of this formula here. So, let's start by writing down the solution. You have a current carrying conductor. How much is the radius? Capital letter R is 4 millimeter. Do not convert it into meter because it may not be necessary. It might cancel out. So, at a distance of 3.6 millimeter from the center of the conductor. So that means small letter R is 3.6 millimeter, and the current is 2 amperes. This is the current in the total wire within R, not within the small radius. That you have to understand. So the question is, how much is the magnetic field strength within this distance, BR? So therefore we say BR equals, according to this formula, mu 0 R times I divided by 2 pi r squared. Now we substitute simply the values. Mu 0, as you remember is 4 pi times 10 to the power of minus 7. Tesla, meter, or ampere. And that times 3.6 millimeter. It's not yet the time to convert it into meters later on. There will come a time. So the current is 2 amperes divided by 2 pi times r squared. R is 4 millimeter times 4 millimeter. You can see, let's start with the units first of all. Since we are talking about magnetic field strength, we have to get Tesla. In the future, you have to convince yourself that when you use only SI units, the final answer will be SI units, and then you can drop all the units and write down, save yourself time, and write down only the SI unit. So, ampere cancels ampere. This millimeter cancels this millimeter. So you see, I have meter and here millimeter. This millimeter has got to be converted into meter, and now you can see meter will cancel meter, and the final answer will be in Tesla. So, how do you do it? It's very simple. Let's do two things at a time. 2 pi cancels 4 pi, you get 2 times 10 to the power of minus 7 and times 3.6 times 2 divided by, remember 2 pi cancels 4 pi and we have only 2. So I have here 4 times 4 millimeter. Milli is a prefix, so to convert it into meter, all you have to do is use 10 to the power of minus 3 for milli. So, Tesla meter. Now you can see meter cancels meter. It was not necessary from the start converting 4 millimeter into meter and squaring it and so on. So, how much does this result become? I think it's a very simple thing. Remove this decimal point. Along with this one, you get 10 to the power of minus 8. With this 10 to the power of minus 3, you get 10 to the power of minus 5. So I have times 10 to the power of minus 5. Something here. What? Tesla. And by 2, 1, by 2, 2. Don't forget that. 2 cancels this 2. 2 times 2, 4 cancels. So by 4, 1, by 4, 9 here. So you have 9 times 10 to the power of minus 5 Tesla. That's the answer. If you want to express it in prefixes, multiply by 10 to the power of minus 1 and multiply by 10, so you get 90 micro Tesla. Alright, another application of Ampere's law, interestingly, is something that we call a solenoid. A solenoid is something that looks like this here, as you can see in the drawing. This one here is what we call a solenoid. It's just a coil which is empty inside. This is another solenoid. You can use solenoids for different purposes. What we are interested in right now is how strong, when the solenoid carries current, how strong is the magnetic field inside the solenoid. Now, I really want you to remember something. It's very important. That when you have a solenoid, inside B is how much? But before that, I want you to remember something. The experiment shows that B here, at the top and around the coil is almost 0, meaning here, at the tip here. B, we call it B outside, is almost equal to 0. So there must be only inside. So how much is B inside a solenoid? Very simple. You apply Ampere's law, which says B is equal to mu 0 I over 2 pi r. And the magnetic fields of each turn adds up. I said each turn and you get one strong magnetic field only inside. So inside, wherever you might be the same. In that case, so ampere circulation sum will give you that B inside somewhere dot a small distance delta L from here up to here, and plus B1 delta L1 plus B2 delta L2 plus until you come here. That means from here up to here. So what do you get here? That equals, ampere says, mu0 times the sum of currents. I told you that the magnetic fields of all the turns add up and give you one uniform strong field. So let's discuss the two separately. If you have n turns, the sum of currents would be mu0 times ni, because the same current is rotating within the turns. How about on the left side? B, I told you it's the same inside from place to place. So you factor out B times, get the sum of delta L's. Delta L I is equal to 1 up to n. You add delta L from here up to here. And this small delta L's naturally give you the length of the coil. So you see how simple it is when you apply Ampere's law. So therefore you get B times L is equal to mu0 times NL. Pronto, therefore B inside the coil only. B inside the solenoid is equal to mu0 and here N I divided by L. Now, interestingly, mu0 N over L sometimes is called turn density, and in physics is given a small letter n as a symbol, at least in your book. So this thing equals mu0 small letter n times I. Capital letter N is number of turns. The small letter n is turn density. So let's look at homework 23. It says find the magnetic field strength inside a current carrying solenoid of 1,500 turns per meter when the current is 4 amperes. So again, B inside equals mu0 n over L times I. The current 4 amperes. mu0 4 pi times 10 to the power of minus 7, this is ampere, Tesla meter per ampere. How about N over L? This 1000, the unit of N is the number of turns. The unit of L is length meter, SI unit. So you're given N over L is equal to 1,500 turns, which is not an actual unit, per meter. That's what you have to write down. N over L is 1,500 meters. So you can see that ampere cancels ampere, meter cancels meter. So the magnetic field inside the solenoid is then equal to 4 pi times 1,500 times 4 times 10 to the power of minus 7. Alright, 4 times 15 gives you 600. And the two zeros, 10 to the power of minus 7, give you 10 to the power of minus 5. So I have only 4, 1,500 is gone. No, 4 times 15 is 60. There were two zeros already. It's 10 to the power of minus 3. Positive 3 with 10 to the power of minus 7. You don't get minus 5. You have to be careful to get minus 4. So I have 6 times 4 pi. That gives you 24 pi, and then times 10 to the power of minus 4 Tesla. This is a bad way of writing down the result because this is not a scientific notation. So the better thing would be, if you're not lazy enough, but if you are given a multiple choice question, use as 3.14 multiplied with 24, you can write it down in scientific notation. Otherwise, for example, if I say just maybe take 10 to the power of minus 1 from here, so you get 2.4, 10 to the power of minus 1 taken from here, 2.4 pi times 10 to the power of minus 3. That becomes millitesla. This is a better expression. This is not wrong answer, but it's neither prefix nor scientific notation. It's just a mixture of different things. Otherwise, you look at the choices and you answer your questions like that. So, one final topic in which we apply Ampere's law is something called a toroid. Well, interestingly, like a solenoid, in a toroid is something that looks like here, the magnetic field in here, and outside the inner radius, and outside is 0. As long as you understand that Ampere's circulation sum is very simple. I repeat, you measure distance from the center of the torus or toroid here, up to distance A, radius A. 0 magnetic field in here. Beyond radius B, again. So, less than A, B0. Beyond A, B0. Where do you find B? Only in here. Ampere's circulation sum. So, how much is the magnetic field inside the toroid? It's very simple. You start from somewhere, the sum of B dot delta L. B is the same everywhere when you travel along this way, so B will be factored out, and the sum of delta L will give you simply B times 2 pi r. But remember, r is greater than small letter a and less than small letter b, meaning within, inside the toroid itself. That gives you mu0 times the sum of currents that you have inside here when you go around. So if you start from here, 1 current, 2 current, 3 current, and so on, that gives you the number of turns since the same current is flowing within the toroid, n times I. Therefore, B inside of the toroid, we simply say B, actually, because it's known that it's inside. B inside is equal to mu0 Ni divided by 2 pi r. That's it. Let's have a look at homework number 24. It says find the magnetic field inside a current carrying toroid at a radius of 5 centimeters with 2,000 turns per meter, carrying a current of 1.2 amperes. So, this is given. This 1,200 turns, and the radius is 5 centimeters, which is the inside. So, if we were going to apply this into mu0 is 4 pi times 10 to the power of minus 7 Tesla meter per ampere, and this one is 1,200 turns, and the current is 1.2 amperes divided by 2 pi r. 2 pi times the radius. The radius is 5 centimeters. Centi is 10 to the power of minus 2. So we easily change it into an SI unit. So how much this result? I don't think it's such a big deal. Ampere cancels ampere, meter cancels meter by 2 pi 1 by 2 pi 2. No, this rough work should be done actually somewhere else. If it's a workout, you're not allowed to do it there. So you get 2 times the numbers first. 1,200 times 1.2 times 10 to the power of minus 7 divided by 5 times 10 to the power of minus 2. So let's remove decimals, they are not good. 10 to the power of minus 1 from here. With this one, 10 to the power of minus 8. 10 to the power of minus 8 divided by 10 minus 2 gives you 10 to the power of minus 6, isn't that? As we have done earlier. We have 2 zeros here. So the better thing would be here to write down 10 to the power of minus 4. Alright? Positive 2, minus 1, positive 1, negative 6, minus 2 again, negative 4. So what do we have here? 2, 12, 12 divided by 5. I suggest multiply by 2 the denominator and multiply by 2 in the numerator too, as we have done earlier. 2 times 5 gives you 10. And so when it comes to the numerator, it becomes negative 1, and this one becomes then 10 to the power of minus 5. I run out of space, alright? Be careful. So let me remove what I wrote down earlier. We are on the last leg of Unit 7, the mighty AC circuit, power in AC circuits. There are many simple trigonometric equations, number 1, and 1 or 2 integrations. I will start with the simplest one, the one you see in front of you, the integration. Later on, in the calculation of power in an AC circuit, will come to a formula where you get cos of 2 omega t dt over one cycle, over one period, from 0 up to period t. Again, sine of 2 omega t dt from 0
when the current starts from some position, when you start rotating the generator, goes around and comes back to the same starting point, that is one period. So simple mathematics shows that over one cycle, cos theta is equal to 0. It doesn't matter what you have to omega t, that will come later on. How we got to omega t will come later on. But no matter what you have in there, cos alpha, cos theta, over one cycle is equal to 0. Sine as well. That's one thing. So if you remember that, we go over to what is power. At the top, power means, as you have learned in grade 7, work done in a given time, or the rate of consumption of energy, W over T. From the electrostatics definition of voltage, work done over transporter charge, and also in unit 5 maybe, or as well as unit 4 of grade 12, current means the flow of charge over time. Then in electricity, work becomes voltage times current times time. That's what you see here. So if you substitute for work the electrical formula, voltage times current times time, and then you divide it by time to get power, you get power means voltage times current. That's what you see here. In electricity, it's just known, starting from grade 8, power means voltage times current. But now, I want you to take care about a minor thing. When you are rotating the generator inside a magnetic field continuously at a constant speed, then you get sinusoidal current and sinusoidal voltage. You're rotating it continuously means the value of energy is changing, the value of power too is changing. So we say power is, instead of saying power is equal to work over time, it says delta W over delta T gives you power when work and time change, or when work changes with the time. When it changes continuously in a very, very small time interval, the delta goes over to D, differentiation. So instead of delta W over delta T, we go over to dW over dt. So we come to the concept of differentiation and integration. So dW over dt, when it changes very quickly, gives you instantaneous power. Whether average or instantaneous, power is always V times I. So here we multiply instantaneous voltage by instantaneous current, because the generator is continuously rotating. I mean, the loop is changing continuously in the magnetic field. Okay, the coil in which we induce voltage. Voltage is equal to sinusoidal V0 sine omega t. Current is equal to sine omega t, but this is a little bit difficult. All of what I'm telling you is very simple. We have instantaneous voltage to be multiplied by instantaneous current. What do we write there? I don't know. You can pick, you decide anything you want, but there is a general formula. What makes things difficult? Are we talking about a pure R circuit? Are you talking about a pure L circuit, a pure C circuit, LC circuit, or LC circuit? In a pure R circuit, for example, there is no phase difference between current and voltage. So what do you write here? Sine omega t, V0 sine omega t for voltage, and I0 sine omega t for current. If you have a pure L circuit, you write down since the voltage is leading the current by 90 degrees, V0 sine you can write either V0 cos omega t times I0 sine omega t, which you will see later on written like that, or which is the same thing mathematically. You check it for yourself. You get V0 sine omega t times I0 sine omega t minus phi. Phi is the phase angle when voltage leading here, and it's here that you come with some simple trigonometric formulae introduction. And I appeal to your knowledge of cos of A plus B and sine of A plus B. Instead of A, we take the phase angle of B, for example, we take phi, and we take the circuit angle omega times t. Where do you find the loop rotating in the magnetic field in time t? Omega times t. So if you take omega t like as A and phi as B, sine of A minus B, what does that give you? Cos A times sine B minus cos B sine A, and here you have a minus sign. That you're going to make this knowledge of yours, make use of that knowledge, okay? So here you have sine omega t, one factor. But let's go through things step by step. V0 sine omega t, I0 sine omega t minus phi, meaning we don't know what we have in the circuit, and there is a phase angle between current and voltage leading phi. Phi is called the phase angle. Now you go over to the mathematics. You multiply out this and multiply it by this sign. What do you get here? V0 sine omega t I0 minus phi sine omega t cos phi minus sine phi cos omega t. That's what you get. So V0 and I0 are numbers. You bring them to the front, and the multiplication of this thing here and this thing here gives you sine phi times sine omega t times cos omega t. But there is a factor too. There is another term at the front. Eventually, you have V0 I0 cos phi times a half of minus cos to omega t minus sine phi times half of sine to omega t. Where do these cos to omega t and half and so on come from? It's very simple. Let me show you two simple things. First of all, cos squared A plus sine squared A is equal to 1. That's one point. Number two, cos of A plus B is equal to cos A times cos B minus sine A times sine B. Let's say B and A are equal. Then what do I get? I get cos of 2A. So what does that give me? Cos of 2A gives you cos A again. Cos squared A, and it gives you minus sine A sine B. It gives you minus sine squared A. In the place of B, you write down A. So you get cos of 2A gives you cos squared A minus sine squared A. From cos squared A plus sine squared A, you have sine squared A is equal to 1 minus cos squared A. So if you substitute that, wait a minute. I'm going to get a free page. For example, this. cos of 2a is equal to cos squared a minus sine squared a, and this one is equal to cos squared a minus 1 minus cos squared a, because you remember cos squared a plus sine squared a is equal to 1. So sine squared a goes to the cos squared a goes to the back. So I get 1 minus cos squared a. So the minus minus makes it plus, and you get 2 times cos squared a minus 1. So if you solve for cos squared a here, therefore, what do you get here? Cos squared a, when we come across it somewhere in the future. In the place of a, I'm going to use omega t. I'm just showing you the mathematics that is something that you can do. The 1 goes to the left, it becomes plus. So I have 1 plus cos of 2a, and there is a 2 in front of it. So I get divided by 2, and here I get a half. That's it. So cos squared a is equal to a half plus a half of cos of 2a. And if you remember sine plus b, sine a plus b is equal to cos a sine b plus, I said not minus, plus cos b sine a. And if b and a are equal, then you get sine of ta is equal to twice cos a sine a. So if you follow this thing and you make use of this one, eventually you come to this conclusion. Cos squared, I'm going to cancel it. There's an eraser over here. It can be erased out, but I don't want to do that. Let's simply go over to sine squared a. So you get sine squared a is equal to a half. You just have to believe me. You can carry out the mathematics yourself by yourself. You get minus a half of sine of 2a. These two things, you really need their knowledge. If I have, for example, cos squared omega t, you have a half plus a half cos of twice omega t. A is simply mathematically done, any angle. For me now, the angle is omega times t, the generator rotating inside the magnetic field. Okay? So, sine squared a is equal to a half minus half of sine 2a, meaning half minus, when I have omega t in this place, a half minus sine of 2 omega t. I hope you remember this thing. I'm going to go forward. To lose up. You see this picture here? It seems to be a little bit intimidating, isn't it? But with your mathematical knowledge, you can easily master this thing. So finally, you see instantaneous power, and you integrate, let me see here. You substitute for sine omega t 2 times sine omega t minus 5 there, and you look at the mathematics, you get cos pi b0 I0 minus, is these 3 terms you see there. This one, this one, this one you find there. And that all is dw divided by dt. So when you take dt to the right, you have this term, and this term here, sine phi sine of 2 omega t, multiplied by dt. When you take them out separately, you have dt cos pi dt here, cos 2 omega t dt here, sine 2 omega t dt here. Please do it on your own. It's so damn and simple. But in the end, I want you to remember only the result. It's so simple. Okay, so I had dw over dt, instantaneous power, v times I. This is my result of VI. The three terms are my result of V times R. I have now dW alone, dt came to the right. What do? I integrate over one cycle from 0 up to W, starting at time 0, energy 0. At time t, some value W. And dt, V0 is a number, it's just peak voltage, I0 is peak current. The cos phi is a phase angle, it's a constant phase angle depending what you have. If you have a resistor, phi is 0. If you have an inductor, it's 90 degrees. If you have a capacitor, minus 90 degrees because the current is leading. So phi is fixed. What is changing is the time, and there as a factor omega t. So the time is changing accordingly. Then wherever you have time, things change. So I have only two terms that change then, the upper one and the lower one, with the cos to omega t and sine to omega t. They are the only two changing. So mathematically, when you integrate dt, cos phi being a constant and V0 as a being constant along with half, they will be brought to the front, and I have dt. It's just like saying integration of mathematically dx. When you integrate dx, what do you get? You simply get x and plus some constant. But if I have write down lower border and upper border here, I don't get a constant. I get x. X upper one substituted minus x lower one. At time 0 here, you get, see, I have here half V0 cos 0 times dt over one period is simply capital letter T times T. That's what you see here, capital letter T. These ones, I have V0 I0 cos phi, the integration of cos 2 omega t over one cycle. And the lower term, I have V0 I0 sin phi, sine 2 omega t integrated over one cycle. When we started about 5 minutes ago, I told you this thing there. When you integrate sine 2 omega t over one cycle and cos 2 over one cycle, you get this. So the sine term and the cos term disappear. You'll be left with only a half of V0 I0 cos phi and times period. So the period, ladies and gentlemen, you take it to the left. When you divide, you get omega over t. I mean work over t, work, not omega, W over t. W is energy divided by time. Since t is large, we don't call this one work divided by time instantaneous, we call it average. So average power is simply equal to a half of V0 I0 cos phi. What do you supply the power to? Depending on that, we have, in the future, you will see three types of powers. Are you supplying it to a resistor? What happens to the phase angle? In the case of a resistor, we say that the angle between current and voltage is 0 degree, and cos 0 degree is 1. So the average power, if you have simply a resistor, becomes V peak voltage times a half of peak voltage times peak current. Very simple mathematics to be carried over. This is some technical problem. There is something in here. Average power is simply equal to a half of V0 I0 cos phi. Don't forget this. That's all. I'll write it down again here. P average is equal to a half of peak voltage times peak current times cos phi. So where does this phi come from? Because we have it because we have an AC, and therefore in an AC, cos phi is called power factor. That's what you see here written in red. Cos phi is power factor. So if you follow me, and if you tell yourself this is really something simple that I can understand, I will ask you one simple question. I'll tell you one, I'll ask you the other. If somebody asks me how much is the power factor in an RC, RLC, in an AC circuit, you have simply a resistor there. In a pure RAC circuit, how much is the power factor? I think very quickly, I say phi is the phase angle, it's the angle between current and voltage. In the case of a resistor, it is equal to 0 degree. So pronto, I ask myself, how much is cos 0 degree? Cos 0 degree is 1. Thus, in a pure resistor circuit, the power factor is 1. It's your turn to answer two simple questions. How much is the power factor in a pure L circuit where you have only inductor? How much is the power factor? Anybody there? Come on now. Are you listening or did you go for lunch? Bamnet, I saw some names, Jonathan, and I also saw Iman and others as well. How much is the power factor in a pure inductor circuit or in a pure capacitor circuit? Let me assume that you're there and let me tell you the answer. If we're in a pure inductor circuit, the voltage leads current by 90 degrees and the phase angle is 90 degrees. Cos 90 degree is 0. So the power factor is 0. So that means the average power is 0. What did that mean and so on? We'll discuss that on Wednesday. But now I just want to know whether you were listening, if you have questions, and so on. Come on, say something. I'm going to stop now. Where does the problem lie? Pure circuit. Are you asking questions? Well, Hermes, Jonathan, Noamin, Timbita, Bemnet, Jonathan. Is this thing difficult? You don't understand it? Or what is it? Yeah, come on. Yeah, say something. We're going to continue with this thing on Wednesday. Power in an AC circuit. And the trigonometry is going to be there. I want you to practice how much is cos of 2a, how much is sine of 2a. Start from cos of a plus b, sine of a plus b, and then go through what we did today. I hope you have the notes with you. Yeah, say something. Yeah? Jonathan? Hermes? Okay. Invite them. No, we're going to stop. So, since you're not responding, and I'm not sure whether you understand or not, and you're not asking anything, I can't wait more than that because the person working at my side, he wants to go for lunch. If it was up to me, I would have waited for 2 more answers until you say something. Don't you understand AC circuit? Do you have any special request? What is it? I have to know what your problems are so that I can help you. You can't simply drop physics because it's one of, as you saw last year, it's one of the most important subjects. And I cannot accept that you don't understand this thing. If you don't, tell me where. Ask. I will explain. What do we do? Let me tell you something. I see 7 students in front of me. Bemnet Binim again. There's Hermes. There is Jonathan. There is Nuhamin. And there is Timbita. None of you cares answer my question. There were about 12 of you when we began, and maybe the 5 were gone, and only the 7 of you remain. So we are going to continue with this power thing. It's a must. I cannot skip it. Yeah, yeah.
On the AC
What do we do?
problem.
Yeah?
On the AC problem.
Yeah, but may we go back and explain? May I go and explain something there, or shall we continue with that power thing, 7.4,
Yes,
and discuss?
on the power thing. On the power thing.
Shall we continue next Wednesday?
Yes, Mr.
Okay, then please, until we meet on Wednesday, let me ask you, beg you rather, one simple thing. Take mathematically cos of A plus B. How much does it give you? Cos squared, cos A, cos B minus sin A, sin B. Therefore, when A and B are equal, how much is cos of 2A? Again, how much does sine of A plus B give you? And when we set A and B equal, sine of 2A, how much does it become? And not only that, please, in the first quadrant, cos, whether it's in the first quadrant and the fourth quadrant, are equal. Cos A and cos of minus A are equal. But sine A and minus sine A are not equal. That too, look at all such simple trigonometric problems and come prepared on Wednesday. Please, please, I'll be waiting for you. See you then.
Okay.
I wish you, yeah, see it. I wish you good luck. And take care of yourself as well. Thank you very much, Mr. Students, welcome to our afternoon class. There aren't many students, but I think we can't wait anymore. I hope that you hear what I'm saying. So we come to now 7.3 alternating current, but before we come to that, there are many important things which you must understand. You understand you do, but I hope that you remember that current produces a magnetic field. And then if current produces a magnetic field and the search was on, last time I told you in 1719, but actually it was in 1819, that purposely people were looking if a magnetic field will induce current, and it was Faraday who 1831, not 1731, 1831 discovered that a changing magnetic field induces current. And then right after that, maybe in the same year, a person called Lenz, either a Russian or a German, I don't know, he found out that when current is induced and it has its own magnetic field, it opposes the magnetic field that causes it. So we simply say that induced current opposes change of flux. So, and then when a wire, we said that when a wire cuts across a magnetic field, that the change in flux induces voltage across the ends of the wire. Then you come to the idea, if I make it a sort of a coil, since induced current opposes the change of flux, when the wire cuts the magnetic field in one direction, if current flows, let's say, towards east, when it cuts it in the opposite direction, current will flow towards west. And from that simple idea, people came to the conclusion that if we make a coil and rotate it in a magnetic field, we get a continuous current. And that what we get is an alternating current. But the alternating current you get outside the magnetic field using brushes and commutators, you can make it a DC, or using slip rings and brushes, you can make it AC. So there are two types of generators, DC generator and AC generator. Today, we discuss AC generator and AC current, some properties of it. You see, experiments showed that when you rotate a coil in a magnetic field at a constant angular speed, the current that you get induced as well as the voltage becomes sinusoidal. Sinusoidal means something described by the equation y equals y0 times mathematically, so to say, sine x. If it's in this form, then y is the instantaneous value, y0 is called the amplitude. Either this or y equals y0 cos x. Mathematically, I'm saying. Either sine or cos, such a value is called sinusoidal. We say y sinusoidal. So what do we have in the place of y in physics? We have current, we have voltage, and later on you'll see that we also have power. But first of all, current. When you have a current, since it's changing, one moment becomes 0, next moment you get maximum value, and it comes down to 0, and so on. And you know that current has a heating effect, and you have to pay money for the electricity that you used as well. What are you going to use in calculations? The 0, the maximum, the average? Well, people discovered experimentally and then proved it mathematically that when we use something called effective voltage or effective current, it has the same heating effect as a DC voltage. That's it. So what is effective current? I told you, it is a current that has an equal heating effect as a DC current. In the same way, the voltage as well. So if, or since current is sinusoidal and is changing in magnitude continuously, how do you get effective current? Well, it is very simple. People discovered that when you take the current, you square it over one period, 0, some average value in between, maximum value, which we call the amplitude, again decreasing, going to 0, changing direction in the opposite direction current flowing. You square it. You square it so that all negative values become positive. And then the bar means average. First, you square the current, then you determine the average. Since we're looking for the current and not the square, then finally you determine the square root. The current that you get in such a process is called effective current, but it has also a mathematical name. We call it RMS current. What does R stand for? What you see from outside. R stands for root. M stands for the bar, average. Mathematically, there is another word for that, M, mean. And then S stands for square. So the name is giving you the mathematical process, but in physics, we simply call it effective. Later on, we'll use only the mathematical name, RMS. But don't forget, effective current and RMS current mean the same thing. First one, effective, means it's a physics name, and the RMS is the mathematical name. So you take the current and square it. You see here, I0, sine omega t, the whole thing squared. What do you see here? I0 is the amplitude. It doesn't change with the time, it's constant. So you square it, and do the square root, you get I0. But the interesting thing is, what about sine omega t? Well, how far does your mathematics extend? When you square sine theta over 360 degrees, let's say sine 0 degrees, sine 5 degrees, sine 10 degrees, sine 20 degrees, and so on, you come back to 360 degrees. Why don't you try it yourself? Add about 20 angles of sine, square it, determine the average, and determine the square root. In the end, you'll get, when you square sines over one cycle, you get a half. And the square root of a half, I'm sure I told you in the classroom that a half is a decimal number, 0.5, and the square root of a decimal number is bigger than the number itself. And so please, if in the meantime you feel like asking a question, please do so. I'm simply continuing because you're not reacting, you're not asking, you're not saying anything. So I was trying to tell you, you take sine theta and give for theta any angle starting from 0 until you reach 360 degrees, take at least 20 numbers, square, and add them. Determine the average. You'll get something like approximately a half. Here is exactly a half. And then the square root of a half, 0.5, gives you 0.07 and so on. So the RMS value is root half of the peak voltage. Numerically, 0.707 V0 for the voltage, or 0.07 of the peak current. So there's a simple question here now. An AC source has a peak current of 2.5 ampere and peak voltage of 24 volts. Find its IRMS and VRMS respectively. Once you understood what RMS current means, what RMS voltage means, and its mathematical process, I think this is just a child's play. For example, IRMS equals root of half times I0. You can answer it orally. So, and square root of half is approximately 0.7 times, you're given here 2.5 peak current times 2.5. So that gives you 7 times 5 is 35, 7 times 2 is 14, 17, you get 2 decimal places, 1.75 ampere. That is the RMS current, which is comparable to the DC current. You can do the same thing for the voltage. The answer of this homework question, for every homework question you find in this note, at the end of the note, you're given the answer. All right, shall we go forward? The interesting thing is in AC circuits, there are 3 interesting devices or electrical objects which we have to discuss in relation to AC current. The first one, as you know, is a resistor. The second one is an inductor. And the third one is a capacitor. How do these electrical devices behave when you supply them an AC? And we discussed 7 circuits, as you see in the picture here. There's a pure R circuit, a pure L circuit too, a pure capacitor circuit, a pure then a combination of resistor, inductor, and then a combination of resistor and capacitor, and then a combination of inductor and capacitor, finally a combination of all. But in the combination of any one of these, we don't discuss parallel combination. Why not? Because it's not in your curriculum. We discuss only, and it's also interesting, only series combination. Yep.
Mister?
Yeah.
By my opinion, everybody here is stupid.
Why? Hello. Hello. Are you Dagmai? Everybody, I hope you are there. These are very simple things. Do not make an elephant out of a mole, as they say. It's very simple. When you have a resistor connected to a generator, what happens? I mean, how does current flow? The coil that you see here is called an inductor. We discussed that last time. Remember, a coil simply has an inductance, therefore the coil is called an inductor. And this is the symbol of a capacitor. You connect it to a resistor. I'll go step by step and explain things to you. It's really very simple. How does the current and how does the voltage behave? And then later on, the power too. That's what we discussed. It's very simple. So we'll have 7 simple AC circuit. A pure resistor circuit, a pure inductor AC circuit, a pure capacitor AC circuit 3, an RL series AC circuit, an RC series AC circuit 5, an LC series AC circuit, and an RLC series AC circuit. R stands for resistance, L stands for self-inductance, C stands for capacitance. Ladies and gentlemen, it's very, very simple. The interesting thing starts right now. In grade 10, if you remember, you learned about resistance. Resistance means to oppose. When current flows, the electrons are being hindered from flowing. Why? Maybe you didn't discuss it at the time. The electrons collide with the atoms of the wire through which they flow. That we call resistance. Now we have another type of opposition to the flow of current. You'll see later on as we discuss. For example, one simple example. Take a capacitor. Capacitor has got 2 plates. Let's say one of the plates is connected to the negative terminal of a battery. The other one plate is connected to the positive terminal. And even the first electron comes and lands on the plate of the capacitor. Then the next coming electron finds an opposition. How? Because in nature, you know that like charges repel each other. But since the coming electron comes with a higher push than the electron which was already there, in spite of the resistance, or in spite of the opposition, the second electron comes. And the 2 electrons together repel the third coming electron. And so on the process continues. Opposition. But this time, it's not a collision. We say the electric field is opposing the flow of current. In the same way, when you have a coil, it produces a magnetic field. And the magnetic field opposes the flow of current because the magnetic field has a flux. As the number of electrons increase, current increases, the flux increases. Meaning flux is increasing means it's changing. So the changing flux opposes the oncoming or the flow of current, the oncoming electrons. All right? So there is an opposition to the flow of current in an inductor due to the magnetic field. And there's an opposition to the flow of current in a capacitor due to the electric field. And there's an opposition to the flow of current in a resistance due to the collision of the electrons with the atoms of the wire through which they flow. So you see, your knowledge of electricity increased tremendously now. Instead of calling it, if there is something that strives to stop or hinder the flow of current, instead of calling it resistance, we try to find out what is the reason. And we give it a name accordingly. If the opposition is due to collision, we call it resistance. If the opposition is due to a magnetic field, we call it inductive reactance. Yes, in the place of resistance, we have now a new word. It's called reactance. The two, reactance, contains two parts: opposition due to magnetic field and opposition due to an electric field. If the opposition is due to a magnetic field, it's called inductive reactance. If it's due to electric field, we call it capacitive reactance. I think the names too are sensible. Now, I told you earlier here that we can have a resistor and an inductor combined, or a resistor and a capacitor combined. So, So I think, as you see here, you expect a name, a new name for the combination of resistance and reactance. And the new name that people give it is impedance. So impedance is the opposition to the flow of current, both due to resistance and reactance. When you hear the word impedance, you automatically know that in the electric circuit, there is a resistance and there is either an inductor or a capacitor or maybe both. If only an inductor or a capacitor is there, the opposition to the flow of current is called reactance. If only an inductor and a capacitor are there, we simply call it reactance. The symbol for resistance is capital letter R. The symbol for reactance is capital X. And the symbol for impedance is capital letter Z. All right? Since we have two types of reactance, you can see we give the subscript L and C. I'm sure, even if I don't tell you, by now you understand that subscript C stands for capacitive and subscript L stands for inductive. Now, in grade 10, you have learned that resistance is defined as voltage over current, even if it was a constant of proportionality. Remember grade 10 physics, Ohm's law? That the voltage is, the current is directly proportional to the voltage, so we turn it around and get voltage is directly proportional to the current, meaning if you want more current, you need more voltage and so on. And the constant of proportionality was R. Using that equation, we defined in grade 10 MA, we defined R, which was a constant of proportionality, as voltage over current. Exactly the same thing we apply here. Impedance is voltage over current, resistance is voltage over current, reactance too is voltage over current. That's all. But I'm sure you're going to ask yourself, if I say, for example, reactance is, or resistance is voltage over current, since in AC we have a sinusoidal current and a sinusoidal voltage, at some moment the voltage becomes zero and the current becomes zero. Are we going to divide 0 over 0? No. All of them are defined as effective voltage over effective current. I said all four. What all four? Resistance, inductive reactance, capacitive reactance, and impedance. Here you begin to learn higher physics, in my opinion, and something very, very interesting begins. you follow me quietly. I mean, not talking, I don't mean that. You just try to convince yourself that you really understand this and this is something elementary. Yes, indeed, it is elementary because it was something discovered by Faraday and his friends around 1831, more than 190, almost 200 years ago, where people were not that much mathematically sophisticated. And they understand this elementary thing. It's very simple. I'm going to show you some piece of wood which we are going to apply in the future. Here, this piece of wood, we are going to use it as a vector because, hello man, are you calling me? We are going to use it as a vector because current and voltage are going to be treated as vectors. But since both current and voltage are sinusoidal, meaning their value is changing continuously, then to show the changing value in physics, we introduce something called a phasor. You take the x-axis as the reference line. I'm also going to raise it in the video. X-axis as a reference line. And then on the y-axis, we are going to look at the projection of either this current or voltage. Because, just a moment, please. Because both current and voltage are sinusoidal. That means their value is changing continuously. So starting from the x-axis, any projection on the y-axis gives you the instantaneous value of current, or if you're talking about the instantaneous value of voltage. Such a rotating current, we are going to rotate it like this, starting from the reference line, x-axis. We are going to rotate it like that. Such a rotating current is called a phasor. For example, if the phasor represents current, the length of this piece of wood, or which we treat as an arrow, phasor means a rotating vector, that's all. What is rotating? Two things, current and voltage. But there are, three voltages. The voltage of a resistor, the voltage of a capacitor, the voltage of an inductor. And when you have a combination of two or more, then we will use a resultant voltage. We'll treat it as a vector addition, that's all. So, for example, at 45 degrees, how much is the current? This angle being 45 degrees is projection. This represents the length of this piece of wood, or the phasor, or the arrow, represents the maximum current. That's amplitude. So, at 45 degrees, projection. Now you can understand when you are at 0 degree, you are on the x-axis, the projection on the y-axis gives you 0, meaning there is no current. The instantaneous current is 0. I'm sure by now you're going to understand where I'm heading to. If you are at 90 degrees, the projection of the arrow or the phasor on the y-axis gives you the maximum, the peak value itself. Then when the angle goes over to 100 degrees and so on, the value of current or voltage will keep on decreasing. Okay. So, good afternoon, students. There was something I asked you to do last time, and I'm sure you can prepare today. We have to finish this thing today, come what may. Cos of 2a cos squared a plus sine squared a. This is one identity that we need. And cos of 2a, I'm sure, is equal to cos squared a minus sine squared a. This was what I asked you to be prepared with. And let me find an empty page over here. Wait, we'll continue. Empty page. Yes. Okay. And the other one is sine of a plus b. Starting from that, this thing equals cos a sine b plus cos b sine a. We need all that. So when a equals b, you have sine of 2a, so you'll be left with cos a sine a. It comes twice, so we have a factor 2. That's one thing. The other one is cos of minus a is equal to simply cos a. And sine of minus a is equal to minus of sine a. All right? With these things in mind, later on we'll change the a angle, a mathematical, into the physics omega times t. So what does cos squared a or sine squared a represent? Let's do one of them, and the other you can do on your own. Cos squared a, if you remember, where cos squared a plus sine squared a is equal to 1. So if you solve for cos squared a, you get 1 minus sine squared a. But we have also this relationship. Cos of 2a is equal to cos squared a minus sine squared a. From that, if you solve for cos squared a, you get cos squared a is equal to cos of 2a plus sine squared a. All right? So you set the two together, and you come eventually to the equation cos squared a is equal to, rearranging and so on, ladies and gentlemen, you get a half plus a half of cos of a, cos of 2a. All right? Again, instead of solving for cos squared a, if you solve for sine squared a, you get 1 minus cos squared a. This sine squared a in the other trigonometric function, and take it from there and set the two here together. What do you, cos squared sine squared a is equal to a half of minus a half of cos of 2a. This is a must. You have to understand this. This is sine, by the way, sine squared. Sine squared gives you minus, cos squared gives you plus. Not only that. You see over here, sine of 2a equals twice cos a sine a. Wherever we might come across cos a times sine a, there is a factor 2 here. If you solve for cos a sine a, you get a half of sine of 2a. You see what I'm doing, or what we are doing now? We are concentrating on cos of 2a and sine of 2a. Why that? I'll tell you later on. So let me take a new page now. I need his technical help. Wait, please. You say, wait, this one here, and what's new here? Okay. So the three equations once again: cos squared a half plus a half of cos of 2a, and sine squared a half of minus a half of cos of 2a, and cos a sine a is equal to a half of sine of 2a. These three mathematical simple relationships of a generator AC circuit is a mathematical term. We have the case where in the place of A, we use omega times time, angular speed times time. So we substitute that in here and use it. So what do we get? We are talking about power. I'm sure you're following me. So power, instantaneous power. Power means voltage times current. So instantaneous power gives you instantaneous voltage and instantaneous current. And we have 7 simple circuits: pure R, pure L, pure C, LC, and so on. Whose voltage and whose current are you talking about? It doesn't matter. We are going to discuss in general terms. As long as the coil turns in a magnetic field at a constant angular speed, I told you that we get induced sinusoidal voltage induced when the ends of the coil are connected. Then induced current flows. All right. So in general terms, then what do we write for a sinusoidal equation? V is equal to V0 sine of omega t and times I0 times sine of omega t. Wait, if we don't know which electrical device we are talking about, what about the phase angles? You know that in the case of a pure resistor, there is no phase difference between voltage and current. And in the case of inductor, the voltage leads current by 90 degrees. In the case of a capacitor, that the current leads voltage by 90 degrees. So what do we do here? There is a simple mathematical formula. Write down here for voltage sine omega t, for current sine omega t minus 5. Do we make it minus or do we make it plus? It doesn't matter. If you're talking about an inductive circuit, it's minus. If you're talking about a capacitive circuit, it's plus. So it doesn't matter as long as we don't know which is which. All right, I'll continue with this. So you'll apply your previous knowledge in here, and we are going to expand this thing. So what do we get? We get here V0, I0, which are simply numbers, times sine of omega t, and here sine omega t minus 5. That is like saying A minus B. So that will give you cos of minus omega t into minus 5. I mean, cos of minus 5 into sine of omega t plus cos of omega t into sine of minus 5. Do not forget what we said about minus earlier. So when you expand this, what do you get? You get V0, I0. I'll take All right, I won't take it into it. All right, sine of omega t into, you see the minus sign here with cos phi, minus phi, cos of minus phi, it becomes minus cos phi. And this one, sine minus phi, it remains as sine phi. Wait. So the other one, the other way around. Cos of minus phi is simply cos phi, whereas sine of minus phi becomes minus sine phi. So you get here cos phi sine omega t minus sine phi cos omega t. So I have three terms here, sine omega t outside a factor I'm in, and there are the two of them here. Let's expand and have a look at them, and we'll get a general formula for instantaneous power. All right, here I get a new page. So instantaneous power then is equal to V0 I0 all right, I hope I remember. Cos phi sine omega t squared. Let me have a look at the previous one. This sine omega t will take it in. Cos phi will be taken out. So you have cos phi V0 I0 cos phi sine squared omega t. And this one, the second term, V0 I0 sine phi is a number. You take it out. So you get V0 I0 sine phi times cos omega t sine omega t. All right? V0 I0 sine phi sine omega t cos omega t. Times cos omega t. Okay, so I'm going to substitute for this one here, and I have here, so it's hardly legible. What you find there is cos omega t times sine omega t. This one has got two terms. This has got just a simple term, a single term. So what do we get? Here you get V0 I0 cos phi times a half minus a half of cos of 2 omega t. And here minus, I have V0 I0 sine phi. Remember, the phase angle does not depend on the type of electrical device that you have. Once you have a fixed phase angle, that doesn't change with time. Just like V0 I0 is a constant, so you can put it at the front as a factor. So I have cos omega t sine omega t, and that we said is equal to a half of sine of 2 omega t. I have three terms now. I'll take out a half at the front. I get a half V0 I0 cos phi along. There is a minus sign here. Minus a half V0 I0 times cos of 2 omega t. And the third term over here, let me bring half at the front, becomes half V0 I0 times sine of 2 omega t. That's it. We're almost there. Okay? This gives you instantaneous power. So what do we do next? Over one cycle, meaning a time span of one period, what happens to the electrical energy supplied to the circuit, whatever it might contain, or to the power? How much power is dissipated? All right. I'll take a new page and do it again. Here. So, again, good. You know that power means work over or energy over time. So instantaneous power is then delta W over delta T, but this time, since it's changing very, very quickly, as I told you last time, we'll go over to the integration or differentiation term, write down dW over dt. That means the instantaneous energy, dW, is equal to instantaneous power times dt. We're almost there. So over one period, we are going to integrate from 0 up to some energy within some cycle, within some period t. So again, here, P instantaneous times delta t, but P instantaneous has now these terms. There are 3 terms in there. You shouldn't forget: a half, V0, I0, cos phi, minus a half, V0, I0, cos phi, times cos of 2 omega t, and minus a half, V0, I0, sine phi times sine of 2 omega t. Remember, we have dW over dt, so I have to take dt to this side. So we write down times dt. I integrated on the left side. We must also integrate on the right side. The integration from 0 up to some period t. Just a moment. Wait for me here. Don't go away. I have your mathematics teacher in front of me, and I'm going to ask him whether you have learned this thing. Differentiation, integration. Thank you very much. All right, ladies and gentlemen, your mathematics teacher tells me that you have learned about this thing. I have to go through this thing quickly over one period. This gives you W on the left side. But on the right side, I have 3 terms. So you see here, I have a half, V0, I0, cos phi. The dt, I'm going to distribute it over the 3 terms here, times dt, and the integration will be written here because V0, I0, cos phi are numbers. And you have learned in mathematics that factors or constants have got to be taken in front of the integration sign. So minus here, a half V0. I want your full attention, ladies and gentlemen. Half cos phi, the integration sign, cos of 2 omega t times this dt. I have a third term, minus a half V0, I0, sine phi, which are all numbers, integration sign, sine of 2 omega t dt. That's it. We're going to integrate over one period, so we write down from 0 up to capital letter T. 0, capital letter T. 0, capital letter T. If you look at the sinusoidal equation of current or voltage, or that of power, you'll see that since it's sinusoidal, below the dividing line and above the dividing line, things are the same. When you add up over one cycle, then therefore this one gives you a 0. And this too, sine 2 omega t over one period too is equal to 0. You can look at the graph and convince yourself. If you need more mathematical convincing, then you have to talk to your mathematics teacher. Though I'm not going to call him now because I'm going to waste my time. So you just have to believe me, over one period, cos of 2 omega t is 0 and sine of 2 omega t is 0. Or look at what you have learned mathematically and substitute capital letter T, subtract and substitute 0 and C. Both of them will give you 0. So what would you be left with? You'll be left with, as you can see over there, the integration of dt. There's nothing in there. Like it's just like saying integration of dx. Integration of dx gives you just x. In the same way, I get here a half v0 I0 cos phi times t. That's it. I'll take another new page and convince you something. So work or the energy consumed is equal to a half v0 I0 cos phi times capital letter T. I'll take T to the dot and divide by T. So you get energy divided by time. That gives you a half V0 I0 cos phi. Work divided by time is power, but this time is not small, it's not instantaneous. So what do we call it? We call it average power. So in a sinusoidal AC circuit, the average power is equal to V0 I0 times cos phi. That was what I showed you last time. Nobody will ask you the derivation, but this you should never forget because we are going to discuss it in general terms now. I'll start with you. If you have a pure R circuit, you know that voltage and current are in phase. How much power does the resistor consume over one cycle? You get half V0 I0 cos phi. Phi is the phase angle. Does anyone among you care? I know that there are two biniums there, Bamnet, and there is a Kudus, and there is Iman. How much is the phase angle when you have a pure R circuit? Does anybody care to answer the question? All right. Nobody says anything. Either you don't hear me or you just keep quiet. I don't know. When you have a pure R circuit, current and voltage are in phase, and the phase angle is 0 degree. And you know mathematically very well that cos 0 degree is 1. So when you have a pure R circuit, average power becomes a half of V0 I0. And let's discuss something mathematically here. A half means square root of half times the square root of half. So one of the square root of halves I'll take with the voltage. The other square root of half, I'll take it with the current, I0. And the square root of half times V0 gives you RMS voltage. Square root of half times I0 gives you 2 RMS current. Therefore, when you have a pure R circuit, the average power is equal to RMS voltage times RMS current, or if you want, is half of V0 peak voltage times peak current. Now it's your turn. I'm going to show you more mathematical things here. See, when you have a pure R circuit, you see here, since current and voltage are in phase, the multiplication of both gives you a positive power in black. When you look at the red and the green sinusoidal curves, current and voltage being in phase, and when you multiply voltage and current, you get simply positive. This is one cycle. That means the power repeats itself twice in a pure R circuit over one cycle of current and voltage. So we say the power oscillates with twice the current frequency. How do you prove that? That is very simple. Mathematically, let me show you. Where is it? Where? Yeah. You see, when you have a pure R circuit, instantaneous power becomes voltage times current. Voltage and current being in phase, you write down V0 sine omega t into I0 sine omega t. I do this for you, and then you have to do the same thing for yourself in the other case. So this thing gives you V0 I0 times sine squared omega t. Did you see that I did not write down any phase angle here minus omega t as I did earlier? The earlier case was a general case. This one is a specific. I have pure R in mind. When you have a pure R here, the phase angle is 0 degrees. That's why I left it out. So you have sine squared omega t. What does sine squared omega t represent, or what is it equal to? That equals V0 I0 times, if you remember, a half minus a half of sine of 2 omega t. When we expand this thing here, you get a half V0 I0 minus a half V0 I0 sine of 2 omega t. So this is instantaneous power when you have a pure R circuit. If you integrate over one period, this one does not disappear, it's a number, and you get times period. But the second term contains sine of 2 omega t, and over one period, it will give you 0. Yes, that's good, but that's not the main point. The main point is the presence of this 2 omega t tells you that the power in the case of a pure R circuit changes with twice the frequency of the current circuit. Where is the current circuit? It is in omega. Omega means 2 pi times frequency, and that frequency is the frequency of the current. Or you can call it, if you want, the frequency of the voltage too. So now this one represents power. You have 2 omega t. Therefore, the frequency of power is twice the frequency of the current, or twice the frequency of power. I mean voltage. That's what you have to know. I'm done. I'm going to take you to the other circuit. And look at this thing here. One cycle of the current and the voltage, green and red lines, the black line, one cycle repeats itself 2 cycles. So that tells you about graphically and mathematically that the frequency of power is twice the frequency of current. That's it, ladies and gentlemen. You also find it in the notes. Not only that, since average power is equal to a half V0 I0, you will find here at the bottom written that it does not disappear. The average power delivered by a source is converted into internal energy. In the case of a resistor, it gets hot. Remember what we discussed under unit 1? That's why it says internal energy. So what happens if you have a pure L circuit or a pure C circuit? It doesn't matter, pure L or pure C or LC. God bless you, Mr. In the case of a pure L circuit, you know that the voltage leads current by 90 degrees. So the phase angle is 90 degrees. All right? So what happens to the instantaneous power? I mean, the general formula, P average is equal to a half of V0 I0 times cos phi. That's the average power. The average power means over one cycle. You have here cos phi, and phi is equal to 90 degrees. You all know, I'm 100% sure, you all know that cos 90 degree is equal to 0. So you have the average power in the case of pure L circuit is equal to 0 over one cycle. What happens if it was a pure C circuit? The same thing, that the current leads, doesn't matter. The phase angle is 90 degrees. So cos 90 degree gives you again 0. So in the case of a pure L circuit 2, the average power over one cycle is equal to 0. How about an LC circuit? There, either you get inductive or capacitive circuit. If both are equal, and that is resonance. We don't discuss anything there. Resonance, no power is consumed. So in the case of an LC circuit too, the current is in the middle. Remember? VL0, VC0, and this is the circuit current I0. So the phase angle between current and voltage, if it's inductive, you have VL0 minus VC0, it would be 90 degrees. If it's a capacitive circuit, you have VC0 minus VL0. Again, the current is leading, you get 90 degrees. So in the case of an LC circuit too, the phase angle is 90 degrees. And cos 90 degrees 0. There too, over one cycle, the average power is 0. What does that mean for you? What you see in front of you, for example, in the case of a pure L circuit, if you look at the green one there, the green one, the current curve over one cycle, the power once, again twice, it oscillates at twice the frequency of the current, meaning the frequency of power in a pure L circuit, in a pure C circuit, in an LC circuit is equal to twice the frequency of the current. The mathematics, already we have done it. You have to look at it again. All right, what does that mean then, that the average power is 0 means? When the current comes in one direction, it opposes it, and there is an opposition, and it stores, in the case of an inductor, in its magnetic field. In the case of a capacitor, between the plates, in its electric field, it stores energy. When the current and voltage change direction, it gives you back what it stored. So it doesn't consume. An ideal inductor and an ideal capacitor do not consume energy, do not dissipate energy. They store and they give you back over a quarter cycle. Store, give you back. Store, give you back. So over one period, the average power is 0. That's what it tells you. Well, how about an RLC circuit? And that's what we did in the previous case there. When you have an RLC circuit, remember what we have done with the phasor diagram. In the phasor diagram, remember, we have here current and we have resistor voltage. We had here perpendicular to that inductor voltage and 90 degrees to the current, and on the lower side we had C0 capacitor voltage 90 degrees led by the current. And when we determined the generator voltage V0, remember what we did? From VL0 we subtracted VC0 here, we got some resultant voltage, and then we combined it with the resistor voltage, and the generator voltage was over here. I mean, yeah, generator voltage V0, and the angle is phi. That's what we call phase angle. So there is some phase angle if you have, or when you have an RLC circuit. So the average power remains as a half V0, I0, cos phi. No 0 this time, or no 1. You have just phi. How much is the phase angle phi? That depends on the circuit. But look at the circuit here. It stores, but it doesn't give you back everything. It consumes more energy than it gives you back. So on the lower side is what you see is given back to you. So that means an RLC circuit dissipates energy. It dissipates power, unlike L, C, or LC circuit. Why is that? Because it contains a resistor. And wherever there is a resistor, it dissipates power. It doesn't have an electric field, it doesn't have a magnetic field, and it can't store energy. A resistor simply cannot store energy. It only dissipates power. And that's what the figure tells you and what it looks like. Yeah. Some technical assistance. Nobody there. They left. Okay. So I'm coming to the final stage. This figure is extremely important. It tells you there are 3 types of power. And when you want to get the phase angle, phi, how do you get it? There are 3 equations which you can use. Either you use the oppositions and the resistances or impedance, or you use the peak voltage, or you use the power. So before I continue, there are 6 or 7 students there. I see you. Please ask where things became confusing. If things did not become confusing, and if you don't want to ask, just somebody among you tell me that we shall continue. Otherwise, I would like to know whether you're following me, whether you understand, or you don't understand, if you have questions or so. Come on, please, somebody say something. Do you have any questions? Do you understand what I'm saying? Did you understand the general formula for average power, that half B0 I0 times cos phi? Well, oh my God. No, I'm not going to ask you. There are only 2 students. So, what is it? አንድ ፔሪድ አይደለም 9ኞች ስለዚህ መልካም ቀን This is your physics class for the week. Good afternoon. I missed 1 class last time. There was some misunderstanding, but I'm sorry for that. I hope that you understood Unit 6 of Grade 12 on magnetism. There are some difficulties there because there are a few things which you have to say experimentally, but I'll try to show you on a video if possible on Friday. Otherwise, next week is a promise, a few things regarding the production of or the induction of a magnetic field by a current and the reverse process. Anyway, we have to move forward, and we are now starting Unit 7 of Grade 12. Listen to me carefully. I'm not sure if you're listening to me. Is anybody listening? First of all, can I hear your voice?
Yes.
Oh, sorry, someone.
Yes, Mister.
Very beautiful. So
Yes,
the thing
Mr.
is like this. Listen, the thing is like this. In 1719, a person called Ørsted accidentally discovered that current produces a magnetic field. We also say induce. Then the many things were done, as you know, Biot-Savart, Ampere's law, and so on, which we discussed on the Unit 6. And then at the same time, starting from around 1720, I think, people were asking one simple question. If current can produce a magnetic field, is the reverse process possible? Can a magnetic field induce or produce a current? For about 12 years, people were searching, and a simple person called Faraday came up with the answer around 1731, I think. So now that's what we are going to discuss. How is current induced by a magnetic field? Meaning, if you want light in your home, you don't connect it to a dry cell. There are no batteries. We discussed something that Faraday discovered, and the thing was, in a magnetic field, if you take a wire and move it across the magnetic field, then the ends of the wire serve as the ends of a dry cell or a battery, so to say. So we say magnetic field is induced. So if you connect the ends of the wire to a bulb, the bulb will glow. Okay? So first of all, what does flux mean? What is magnetic field? The formula is given in a quantity of magnetic field lines are called flux in a given area. That's what magnetic flux says at the top. And how much EMF is induced? It depends on the quantity of flux that the wire cuts through. That was what Faraday discovered. It says induced EMF is directly proportional to the rate of change of flux. What I wrote in the numerator is change of flux. Then if you change the proportionality sign into an equality sign, all you get is simply capital letter N, a constant of proportionality. What is N? Well, if you move one wire, you get some. Yes? Yes. If you move a wire across a magnetic field, as I told you, this is the induced EMF is rate of change of flux over delta T. That gives you the speed. And I hope that then you remember flux is V times A times cos theta. It's a dot product of magnetic field strength and area vector. So if a wire induces a magnetic field, a voltage, then you come to the idea, if I use 2 wires, 3 wires, 4 wires, and so on, I'll get more voltage induced. That's true. So what do? You take a single wire and make it into a form of a coil. So that coil, how many turns does it have that it cuts across a magnetic field? That's what we call N, number of turns in a coil. So induced EMF then equals N times rate of change of flux. How fast does the flux change? Then immediately after about, I don't know, a few months of Faraday's discovery, somebody in Germany, I think, came up with an interesting idea. He said the induced EMF opposes the change of flux, meaning when current flows, you know that, I hope, and if you have a coil, that was what I tried to show you last time, the coil produces such a magnetic field. Let me show you a drawing here. A coil, yeah. connected to a current source, the coil produces a magnetic field that looks like that of a bar magnet. If it looks like that of a bar magnet, then we'll have a north pole on one side and a south pole on the other side. We discussed that in my right-hand rule last time. So what did Lenz say? Lenz said the induced EMF, if you connect the ends of the wire, causes an induced current, and when current flows always produces a magnetic field. Let's call it this time induced magnetic field. That induced magnetic field opposes the change of flux, meaning if you have a north pole coming, a north pole will be induced by the flowing current and it will oppose it. If a south pole is coming, a south pole will be induced opposite. That's what Lenz's law says. So generally then we have a single law which comprises Faraday's law as well as Lenz's law. And we write down induced EMF is equal to minus n times rate of change of flux. This minus sign is supposed to show you or to tell you that the magnetic field of the induced current opposes the magnetic field which caused this voltage in the first place. So we say briefly, induced current opposes change of flux. All right, let's go on. All right. And you see here in the drawing, for example, a single wire cutting across the magnetic field. Interestingly, then you get maximum induced EMF when the wire cuts across the magnetic field perpendicularly. The magnet rolls, or I mean the wire rolls and cuts the magnetic field lines. So where is the flux now? If you have a single wire, how does it cut a flux? A flux is quantity of magnetic field lines that are given in a certain area. Well, at the wire rolls, you know, the drawing. Okay, so let's say this is the magnetic field lines downward, and this is the direction in which you roll your wire. So flux means quantity of magnetic field lines in a given area. V is simply magnetic field strength. So which one is the flux? Well, you see, the wire has a certain length, let's say L, and it rolls this way. How much distance does it cover? Let's say the distance is S. So it cut through all the flux in this area. And area means then length times breadth mathematically. The area would be, when we talk about the flux, the length of the wire which cuts across the magnetic field, and the breadth would be the distance covered by the rolling wire. That's what gives you change of area. Rate of change of flux. Flux means B times A. B is constant. Area is changing. So delta A over delta T we get. And delta A is then this area here, the one I just showed you. Length times distance. BA times B, mathematically, at the same. So, how first induced EMF equals Shall we forget the -9 for the time being? N times. You have just a single wire. So you have 1 here. Rate of change of flux over time. Flux means B times A over delta T now. B constant, delta A over delta T. All right? So area means L times L, S. The length is not changing. Now the change of flux is caused by the rolling wire. So you have here B, L times delta S over delta T. But delta S over delta T, this thing here is velocity in physics. So you get here B, L, V. When a single wire cuts across a magnetic field. If the wire is a millimeters long, that doesn't matter. We look only at the length of the wire, which cuts across a uniform magnetic field. Outside the magnetic field, the length of the wire will not be considered. Only the length of the wire within the magnetic field. So we get BLV as an induced EMF. That's how we get the formula BLV. So these are Faraday's law, and let's discuss something interesting here. You have a coil, as you see in the picture. The north pole of a magnet is coming and entering the coil. This is, the solenoid is empty, by the way. It's not a solid thing. So a north pole is approaching. Now, what happens here? Since the flux is changing in the coil, do you know something? EMF is induced due to a change of flux. Whether a magnet moves into a coil or a coil goes towards a magnet, as long as there is a change of flux, it doesn't matter. This time, it's simpler to move the magnet into the coil. But you can do also the reverse process. So north pole is approaching. There's a change of flux in the coil. According to Faraday then, or electromagnetic induction law, voltage will be induced. The ends of the coil are connected. Since the ends are connected, what you see is 0 at the center is a galvanometer. It will show a reading. That means current is flowing. When current flows, a magnetic field will be produced. Since the current is induced, we call also the magnetic field induced magnetic field to differentiate it from the magnet that is from the permanent magnet that's approaching. So when the north pole is approaching, according to length, here a north pole will be induced because the induced current opposes the change of flux. Now you go over to the right-hand rule we discussed last time. If a north pole is induced here, how does the current flow? Well, right-hand rule for induced magnetic field of a coil, you extend your thumb in the direction of north pole, the thumb of right hand, and you hold the coil in your right hand. If you're following me carefully, when the north pole is induced, your fingers are pointing towards you downward. That means the induced current flows from backward to the front. If you stop, there's no change of flux. Induced current disappears. The galvanometer needle comes back to 0. So what do you have to do? If you want to change the flux, you have to move the magnet back. When you move it back, north pole is receding. That's what you see in blue at the bottom. So when it's receding, there is a change of flux. If there is a change of flux, voltage will be induced. Since the ends are connected, there will be current flowing, induced current. When current flows, a magnetic field will be induced. So, and what does the magnetic field look like? Since a north pole is receding, if you are to stop the magnet from moving away, you don't hold it with your hand. You give it a south pole, because south pole and north pole attract each other, meaning you're trying to stop it from moving away. So if this end of the coil is a south pole, the other end of the coil would be a north pole. Why? Because there are no monopoles in nature. Then you go over to the right handle of a coil. If this is a north pole, how was the induced current flowing? You let the thumb of your right hand point in the direction of induced north pole, and you hold the coil in your hands. Now you can see that your fingers of the right hand point away from you and the current flowing out. If you're following me, then you see something very, very interesting, which people discovered for the first time in an electromagnetic induction. In principle, you get an AC. North pole comes, current flows in one direction. North pole recedes, current flows in the opposite direction. You can turn the magnet around and let a south pole come and go away, approach and recede. You see that according to Lenz's law, south pole coming, south pole will be induced, north pole and so on the other side, south pole receding, north pole will be induced, then current in the opposite direction. The current will be flowing back and forth. Now you understand, I hope. That's why we have in the picture here a galvanometer which has got a 0 at the center. When current flows in both directions, it measures current in both directions. So such a galvanometer is different from what we discussed under Unit 5. Such a galvanometer is called a center 0 galvanometer. Shall we continue, or do you have any questions there? Yeah, any questions? Nobody's speaking? Nobody wants to ask?
No.
All right, then we'll continue. If you're following what I was saying, there's a hand over there. It's not my hand. It came from somebody abroad. He is bringing in a North Pole. So the wire is connected to a center 0 of a galvanometer. You have to take this wire as a coil of only one turn. So since a North Pole has got to be induced when the North Pole is approaching, the current then will hold the coil, so to say, the loop in your right hand, and the current will be down. When the North Pole moves back at the red arrow points, then there is a change of flux, and the induced current opposes the receding North Pole, as we said earlier. So you have to put a South Pole over there, and then the North Pole would be on the other side. You hold the single loop in your hand in such a way, the extended thumb points in the direction induced North Pole, and the loop in your hand, your fingers will be pointing upward. I hope you agree with me. Let's go on. They are asking you more questions here. There is a single loop again. A North Pole, as you see here with V, a North Pole is approaching towards a ring. You can take the ring as a coil with a single turn. And the same thing happening now. When the magnet is approaching you, your thumb will point towards it, towards the induced North Pole. So current is flowing up. When the magnet is receding, as you can see in the next picture B, the red arrow points here in the lower picture. That means that the magnet is receding. When it's receding, since it's a North Pole which is receding, and a South Pole will be induced on this cross-sectional area of the ring. And so if this is South Pole, the North Pole would be on the other side. So your fingers again point towards you down. That's what he's showing. Well, from that, you come over to more and more mathematical things. If you see here, BLV, that was what we discussed earlier. We have a single wire in this picture. I'm continuing because you're not asking me any question. I thought that you find it simple and you're following me. Here is an interesting thing. You have a magnet, a single wire is rolling across a magnetic field. Which way does the magnetic field point? You see a B in at the top. B in means the magnetic field is into the page. Under Unit 6, we discussed it. That means magnetic field lines are pointing from you, away from you, into the screen or into the page. So this wire, as I told you, perpendicularly cutting across the magnetic field, maximum flux, because the area will be perpendicular to the area vector, be perpendicular. And that's why B and area would be in the same direction. When B and area in the same direction, the flux would be BL cos 0 degree, and cos 0 degree is 1. That's maximum, okay? But if you change the direction of area or the magnetic field, the area vector and B do not have an angle of 0 degree, then the flux will decrease. Right now in the picture, this wire cuts, as you see with the red arrow, velocity, is rolling towards the right. When it rolls towards the right, it cuts across magnetic field lines, magnetic flux, so to say. Then there is a change of flux in an area. What area? The area which we talked about earlier. L times the distance it covered. That's the area which we take as the change of area. Divided by the time it took to come over here, and change of area over change of t, that gives you, here as you can see, induced EMF for a wire, N delta phi over delta t. And when there is a single wire, N is equal to 1. Now, the interesting thing here is the wires, and the wire is rolling across, along, or on two horizontal wires. So if it's rolling on a wire, there's a physical contact. Induced current then can flow. That's like having, if you go to a shop and buy a dry cell, it has a voltage, but no current is flowing. If you connect the ends of the dry cell with a wire, then current will start to flow. It's up to you what you want to do with the current, whether you'll connect a bulb to it or not, that's a different story. But as long as the ends of the dry cell are connected, current will be flowing. In this picture, that's the point. The ends of the wire are connected. There's a resistor there. The resistor, you can take it as a bulb. So current will flow. And the next question is, which way does the current flow? Can you see from what we discussed earlier? Can you think about it and come up with the answer that the current must be flowing down, meaning the current is flowing in the anti-clockwise direction? If you stop, if you go out of the magnetic field and stop, there will be no induced current. So if you want to have induced current, just as you move a North Pole into out of a coil, you have to roll the wire back and forth. Move it forward to the right and you move it back. When you move it back, definitely there must be an induced current, but in the opposite direction. Current will be flowing up. Think about it until next time and convince yourself that the induced current will be flowing up. There's another thing in the picture. With a black arrow, there's an FB. What is FB? It's a magnetic force caused by a magnetic field. B stands for magnetic field strength. Not the one which is given here. The induced current produces its own magnetic field. And that magnetic field tries to stop your motion towards the right. When you move to, when the wire rolls towards the left, it wants to stop the rolling towards the left. That means the induced magnetic field, so to say, acts in the opposite direction. And all this ties up with the law of conservation of energy. Take time and think over it. But at least the formula BLV, induced EMF, is very simple. It's given over there. Induced EMF is equal to N delta phi over delta T. Delta phi means BA, and you have a single wire, is just one. B is not changing, as you see in the magnetic field. The wire is rolling. That means area is changing. So you have delta A over delta T. Area means the length of the wire within the uniform magnetic field times the distance it covers in the magnetic field in some given time. So you have delta LS over delta T, and L, the length of the wire in the magnetic field is constant. What is changing is only the distance it covers in a given time. So you have V non-changing, L non-changing, delta S changing, delta S over delta T. So in physics, delta S over delta T is the speed with which the wire cuts across a magnetic field. All right, shall we continue?
Yes.
All right, okay. This is some interesting thing. In the previous slides, you saw a magnet moving into and out of a coil, but this time is something different. That magnet actually was a permanent magnet, but we can get a magnet from a different source. From what? From a battery. When you have a battery and you connect the ends, you make a coil, like as you see in the picture here, you get a coil and you have a magnetic field. So I have here a magnetic field, albeit an electromagnet. The other one, you can call it, which we discussed earlier, a permanent magnet. This is an electromagnet. Where are its north pole and where are its south pole? For this coil that you see here, well, we discuss only conventional current. This is the positive terminal of the battery here. Conventional current flows this way. So it goes to the back, comes to down and flows up at the front. Meaning then, conventional current at the front is flowing up. So the north pole would be here. Since there is no monopole, this is the south pole of the magnetic field produced by the current of the battery. Okay? The interesting thing is what you see here. It is a switch. If you turn on the switch, it's as if current is coming, and current is coming means a magnet is approaching. If you open the switch, current is disappearing. Current disappearing means a magnetic field is receding. So let's see if things are consistent with what we discussed earlier. The switch, as you see in this drawing here, the switch, the arrow points down, meaning the switch is turned on. Current is flowing. Current is flowing means conventional current. A south pole is approaching. This south pole approaching, according to length, electromagnetic induction, the induced EMF will oppose, the induced current will oppose this magnetic field. So oppose means when a south pole comes, you have to give it a south pole. If this is a south pole, then the opposite end of this string is a north pole. So you move your thumb towards the north pole in such a way that you hold the coil in your right hand, not the coil. What I mean is the red ring. It's in this one that is current induced. The other coil is the one which produces the magnetic field. It's an electromagnet. So since your fingers are pointing down, meaning induced current is flowing down. Come to the next picture. Until I go over to the next slide, I think you have the notes and you can see it already. If you see the arrow here, it means the switch is open. If the switch is open, which way should induced current flow? It's actually a very simple thing. You can easily convince yourself. When the switch is open, it's as if the south pole is receding. if a south pole is receding, the induced current produces such a magnetic field to stop it, and you stop it with a north pole. If this cross-sectional area of the ring acts as north pole, the other end acts as south pole, so you extend the thumb of your right hand in the direction of induced north pole, and you hold the ring, the single turn coil, so to say, the ring in your right hand, and the fingers are pointing up. So that current is flowing up. Did you convince yourself that in electromagnetic induction, always the motion takes place back and forth, alternating current flows up, down, up, and down? Shall I continue? I hope that we still have some time here. Yeah. All right, this is all what you see, and it's gone with what we have here. By the way, this formula tells you that induced MF depends on the number of turns in the coil or on the magnetic field strength. If the magnetic field strength is changing, if a magnet is coming and going, it's the magnetic field which is changing. Or if it's a wire that is rolling, it depends on the area. How do you roll the wire inside the magnetic field in such a way that the angle between area and B is perpendicular? I mean, between A and B is 0 degree, or do you move it in a different direction? So the angle too affects it. So there are about 3 factors that affect the change of flow, the induced EMF. That's what is written here, the magnetic field B, the area enclosed, and so on. Oh. Now, from this, I don't have a video on this one, but I can prepare a video on AC generator. You can easily come to a conclusion here. Do you see that if one wire cuts down, if current flows in one direction, if the wire returns in the opposite direction, current will be induced in the opposite direction. So if you move up and down, you get current continuously. You see, you come up with the idea that, what if I have a coil? Yeah? And such a way that when one end moves down, the other end moves up. And if current in this one flows, for example, towards this, and this one, it will flow in the opposite direction, and you'll get then a continuous current. Something like this is called a coil. I said only a coil. So it's up to you. Here is a handle here that you see. If you rotate it continuously across a magnetic field, you get current, induced current flowing continuously without any breakup. So you come up with many simple ideas and some technical challenges as well. You increase the number of turns, you increase the quantity of induced EMF. Then you come up with the question or to the idea, how do I turn this coil in the magnetic field continuously? And naturally, this is an engineering rather than physics. You give it an axle, you have a handle there, and you rotate it in the magnetic field. So what type of a current do you get? AC, or can you get also DC? If you are following your grade 10 physics, if you follow 10 physics, whether you get a DC or AC, it depends only on what you have outside. That means outside the magnetic field, if you connect it to what we call, as you see on the left side, a commutator and brush, you get a DC generator induced. That's how you get DC source, by the way, DC generator. But if you connect the ends of the wire which are rotating inside the magnetic, by the way, to rotate the wire inside the magnetic field, I told you you need an axle, you have to wind the wire on the axle, and you have to have a means of rotating it connected to the axle, whether you have a gear or something different. It depends on the engineer. And not only that, talking is so simple, isn't it? What is it? Do you turn it in the air? No, you have to have some support for the coil. So there must be an appropriate rotating coil. That is a technical challenge, but people do so thousands or millions of things. It's not so difficult. Let's go over. Let's continue. Let's go on now. If you connect the ends of the coil to something called that looks like a ring, one end of the wire is continuously connected to one ring, the other end of the coil is connected to another ring, and if you are able to rotate it, the rings are called actually slip rings. Why do we call them slip rings? Because they cannot, well, what do you connect the rings to? Say to a bulb. The bulb cannot afford to rotate with the coil. So what do? You keep the bulb on a table and you make the rolling wire or the rolling coil touch a piece of metal. That piece of metal touches with the coil. And due to that, the piece of metal is called a brush, and the touching circular metal ring is called a slip ring. It just brushes across the metal, and it rolls. So if you have slip rings and brushes, you get an AC generator. If you have a commutator, commutators are two semicircular metals. After a 180-degree turn, it comes to the right, and this one goes to the left. After 180 degrees again, the one that was on this side, it will go to the other side. It will commute back and forth, back and forth. That's why you get the name commutator. Commutator and brushes give you DC generator. Slip rings and brushes give you AC generator. I think that's not a big deal. Yeah. So this is a simple classwork question. It says, find the rate of change of magnetic flux in a coil of 100 turns when the induced EMF is 3.6 volts. All right. You take N 120 turns. Shall we do it? In your solution, you see you have induced EMF is equal to N times rate of change of flux. Did you notice that I didn't write down the minus sign? The minus sign is only interesting when people ask you which way does induced current flow, or people say what type of a pole is induced here. Otherwise, in calculations, we usually drop it because we are interested only in the induced voltage, magnitude, and so on. So here, then this EMF is 3.6 volt, and N is 120 turns, which we don't write down turn. So the question is, how much is the rate of change of flux? This rate of change of flux. Well, you take 120 to the other side, you get 3.6 divided by 120. Do you see that rate of change of flux has the unit of voltage? Maybe you didn't up to now, so that's the time now to see it. So we write down rate of change of flux is equal to 3.6 volts divided by 120. There's a point here. If you remove a decimal point and write down 10 to the power of -1, You take the 0 to the numerator, you get 10 to the power of another minus 1, 10 to the power of minus 2. 36 by 12 gives you 3. 3 times 10 to the power of minus 2. 10 to the power of minus 2, what? Flux. And in the numerator, you have second. Since it has to, the unit has got to be, you have, I mean, in the numerator, volt, and in the numerator, nothing, just volt, done. Number of turns. So rate of change of flux as the unit volt. When you take it to the other side, solve for change of flux. By the way, we got our answer here. The answer to this simple question is the rate of change of flux is 0.03 volt. And then the unit for flux would be delta phi equals time. If you bring time to the other side, the unit is second. That means the unit of flux is volt second. Well, that's our unit. But from what did you get volt second? Into flux, if you remember, is flux VA cos theta. Cos theta is a number, it doesn't have any unit. The unit of V is Tesla. The SI unit of area is meter squared. So that means Tesla meter squared at the same as saying volt second. You can rotate units around and you can think of different things. Let me move forward. Yeah. It's all right, Guru. And that's you, Guru. Did I know? Okay. I mean, shall we simply go forward to this thing, or do you find it a little bit, I don't know, too much theoretically, or, yeah, shall we go forward? Is there something confusing, something which you don't understand? Nothing. I think I have to show you sometime next week or on Friday if possible about induced EMF and so on. Right now, I have to stop here. I'm not sure what you felt about this. Did you appreciate electromagnetic induction? It's really a very, very interesting thing, but we are just the tip of the iceberg. We have to go really very quickly forward. So I'd like to know your opinion. I mean, what do you think? You have to stop here right now. Don't you want to say anything? Did you find it interesting? Did you understand what we discussed? Or is there something confusing?
Good morning, students. I have a small demonstration for you. The objective of today's demonstration is to see which bulb glows brighter when they are connected in parallel and in series. There are two pairs of bulbs of different powers. Here is 40 watt, here is 60 watt, and they are connected in parallel. I'll show you that. Here is a 3 watt bulb, here is a 5 watt bulb. They are connected in series. Now, in parallel, which bulb glows brighter? 60 watt, 40 watt. I think you can see clearly that the one with the higher power glows brighter. How do we know that they are connected in parallel? Simple. Unscrew one of them. For example, this simple power. You see here? Nothing happens because they are connected in parallel. So, let me go to the other one. These two bulbs are connected in series. This is 3 watt, this is 5 watt. Which one glows brighter? Let's see. You see here, the bulb with the lower watt glows much brighter. I have some bonus for you as well. How do we know, first of all, they're connected in series? Simple. Unscrew one of them. Here. You see this? It goes up because they're connected in series. So, what's the bonus? Alright, the bonus, you'll see that when I connect, (3 watt, 40 watt. In series, this glows brighter. But what would you see? Let's see. And the answer, the question you have to answer why now. Look at this. Pronto. The one with the lower watt glows much brighter, but this one is not glowing. Maybe it's not connected. It is. Let me show you. You see? When I unscrew it, everything goes out. It's connected, but why doesn't it glow up? I leave that to you. Thank you very much. This is today's class.
When you turn on the switch, there was in the beginning no current, no magnetic field. Remember, current produces a magnetic field. So when the switch is turned on, the current produces a magnetic field. So now there is a change of flux. This change of flux induces a voltage. What voltage? It already has a battery here. The induced voltage is a voltage which opposes the battery. And so when a coil induces voltage or current in itself, the process is called self-induction. As you can see at the bottom, there are 3 words written there: inductor, induction, inductance. What is it? The induced EMF in the coil is directly proportional to the rate of change of current. If you simply turn on the switch and stop, the induced EMF will disappear. If you open again the switch, then again there will be an induced EMF which wants to stop the going away of the current. So if you turn on and off the switch, there will be a continuous change of flux and there is a continuous induced EMF. The induced EMF is directly proportional then to the rate of change of current of the battery. That is the turning on and off the switch. So the constant proportionality, as you see here, is L. That means how much voltage can the coil induce in itself. It depends on the nature and the type of the coil. This constant of proportionality is given the symbol L in almost all physics books and is called self-inductance. Now you have 3 words. The process of inducing current is called induction. The coil itself is called inductor. And the constant of proportionality is called self-inductance. Unlike what you see in your book, they made a small error there. I'll tell you explicitly what error they made. Induced EMF from the point of current is equal to L delta I over delta T. From the point of view of rate of change of flux, write down N times delta phi over delta T. The same induced EMF is written in 2 different ways. So when you equate the 2, since the time interval is the same, it cancels out, and then you get this formula here. That self-inductance times change of current equals number of turns times change of flux. So what factors affect self-inductance? When you equate the 2, particularly flux means V times A. So you have, for example, if it's only the magnetic field that is changing and not the number of turns and not the area of a coil, then you write down NA delta V. Delta V, as you know, is equal to mu0 N over L times I current. And when you multiply out N times N and so on, you get mu0 times N squared over L times A times delta I on the right side. So delta I and delta I cancel out. So self-inductance, as you can see, is equal to mu0 N squared over the length of the coil L times A. Since N over N is turn density, you get mu0 small letter n turn density squared times LA. What you have in the denominator is L. When you square n, is the thing is like this: n over L is turn density, small letter n. In the numerator, you have n squared. In the denominator, you have only L. If you want to write down n squared turn density, then you have to have one more L in the denominator. So mathematically, we multiply by L in the numerator as well as in the denominator. That's how you get here mu0 turn density, small letter n squared times L times I. It's not a current. This is small letter L, the length of the coil. So here you have a serious warning. The smiling man or laughing, whatever you call it. L depends only on turn density, length of the coil, and cross-sectional area. As it's given in your book, if you go over there and look at it, it does not depend on the flux and it does not depend on the coil. It just depends on the physical properties of the coil only. That's one thing I want you to take care about. All right. There is one small problem here. What's the self-inductance of a coil of 200 turns, where a changing current of 1.5 ampere causes a change in flux of 2.44 times 10 to the power of -5 Weber. This does not mean that self-inductance depends on flux and current. It's just like saying, for example, in unit 5, we say voltage is equal to resistance times current. You can ask how much is the resistance if you divide voltage over current, you know? But resistance is equal to rho L over A. The same thing is happening here. L times change of current equals N times change of flux. So from that, you can get L. This is a simple calculation. So it does not mean that it depends on flux over current. I hope you understand. There is something interesting I want to discuss rather with you, because it concerns some mathematical integration. When you have a coil and current flows in it, in the beginning, it opposes the magnetic field, and once the current starts flowing, the current overrides the opposing magnetic field, and the coil produces a magnetic field in itself. So that magnetic field stores magnetic energy. That's what we call energy stored, and the coil this time is called an inductor, if you want to use it in the form of an inductor to induce current. So how much is the stored energy? Well, you remember electrical power means electrical energy divided by time, and VIT divided by T gives you that electrical power is current times voltage. This time induced voltage. And induced voltage is IL delta I over delta T. If you multiply by delta T left and right, you get instantaneous power times delta T L I di. I, current, voltage, L di over delta T. Delta T is brought over this side. Now, in some given time interval, if you want over one cycle, if you integrate left and right, this gives you the magnetic energy stored in the coil. And this one gives you, on the right side, LIDI. It's just like saying some constant x dx. The integration of x dx gives you a half x squared. So Li is a constant, you get here a half Li squared. A half Li squared is magnetic energy. There is another symbol we use here. Another symbol is capital letter U and subscript V. Capital letter U in physics usually stands for potential energy. So what potential energy is this now? The magnetic potential energy stored in the inductor. So there's a simple question here. It says, what is the magnetic energy stored by the inductor in homework 26 above there? You write down a half Li squared. Why does it say homework 26? It wants to make sure that you know how to work on L, and you get L from homework 26 is some number there, and the current is given here, 2 amperes, and you get some magnetic energy, you know. Now one more interesting topic, which we can do together. Magnetic energy density. The word density in physics, I told you, some physical quantity divided either by length or area or volume. This time is volume. Why? Because magnetic energy is equal to, as you can see here, mu0 n squared A over L times I squared, a half L I squared. All right? And L is equal to mu0 n squared over L A. L is moved to the right, it doesn't matter. And there is I squared here. If you want to write it down in terms of density, term density, n squared n over L, small letter n. N squared would be then small letter n squared times L, and L comes here. May I write it down and show you here? This one gives you a half mu0 n over L, the whole squared. But there is only one single L. So to compensate that, you get times L. A half mu0 n over L, the whole squared, times L times A times I squared. You see now two small things. One, this n over L is term density. So I get now n squared. And you can see that L times A. This is the cross-sectional area of the coil, and L is its length. So mathematically then, L times A gives you volume. So I have here times I squared, and there is a half mu0. So here on the left side is magnetic potential energy. If you take this volume to the right, to the left, I mean, then you get mu b divided by volume, which leaves you with a half times mu0 turn density times I squared. That's horrible, you know, the writing is not so clear. So what you have on the left side is magnetic energy divided by volume. So you understand with me, we call it now magnetic energy density. But the bad thing is the symbol we use for magnetic energy density is again U, but this time small letter U, capital letter N, number of turns, small letter n, turn density, capital letter U, magnetic potential magnetic energy. Small little u, magnetic potential energy density. So U V equals a half mu 0 n squared times I squared. All right? We can do another rearranging here because mu 0 turn density times current is magnetic flux. Not magnetic flux, magnetic flux density B. B equals mu 0 and, oh my God, times I. But there is a square on I, there's a square on, here is a square on turn density. And so I'm sure you come to the conclusion that if I have a square on mu, constant of proportionality, then I can get B squared. Yes, of course you do. So you have here a half B squared. B squared means mu 0 squared times n squared times I squared. But there is only one mu here. So to compensate it, you have to divide the denominator 2 by mu 0. Pronto. Magnetic energy density is very elegant, a simple formula. A half B squared over mu 0. Wait, I need some technical assistance with him. So that's right. So look at homework number 7. It says find the magnetic energy density of an inductor that has a flux density of 0.04 T. Flux density is the correct name of B. B is not called magnetic field strength. It's only in high school we call it like that. Actually, there is another physical quantity called magnetic intensity. The symbol is H. So the correct name for magnetic field strength is magnetic flux density. And later on, we'll give it another name too. This, I think, is the correct plus. It's called also inductance. So magnetic energy density, can you do it here? Mu B is equal to a half B squared over mu 0. Let's do it somewhere else and show you some small error. So magnetic energy density mu B is equal to a half B squared over mu 0. So the required quantity is how much is mu B? That gives you a half times 0.04 Tesla times 0.04 Tesla divided by 4 pi mu 0 times 10 to the power of -7 Tesla meter per ampere and so on. The final answer would be in joule per cubic meter. Write two things now. One, 0.4 means a half times 4 times 10 to the power of -4 divided by 4 pi times 10 to the power of -7 joule per cubic meter. You see, -4 cancels -7 and you get 10 to the power of -3. It's very simple to see. When you take 10 to the power of -3 to the numerator, it becomes 10 to the power of +3. It means 1,000. Don't forget, 1,000, positive, not negative. And there's a mistake in the nuts. So this 4 cancels one of the 4s over here by 2, 1, here by 2, 2. So you get 2 times, oh my God. Can I erase out this? All right, it's my mistake actually. By 2, 1 by 2, 2 times 1 over pi times 10 to the power of positive 3. I would like to go to another page. This one. All right. So you have here 1 over 2, 2 times 1 over pi times 10 to the power of positive 3. Please remember this thing from today onwards. This 1 over pi, to a very good approximation, is equal to 0.32. You don't need any calculators. So 0.32 times 10 to the power of 3. So 10 to the power of minus 2 from here, 10 to the power of positive 3 here, you get a 10. 2 times 32 is 64. 64 times 10 gives you 640 joule per cubic meter. This is the correct answer, not the one given in the notes or in what is sent to you. You can correct it. That's it, ladies and gentlemen. I'm going to go over to 7.2 very quickly. There are also a few things simple things which I want to discuss there. The new one. Yeah, good morning there. I see your face. .7, that's right. Good. So before I start with AC generators and transformers, this has got, not this one, but the other ones have got their own problems. Please remember something. Done. The unit of self-inductance L is called Henry, number 1. Number 2, that self-inductance, unlike what is given in your book under 7.1, it does not depend on voltage, it does not depend on current. Okay? And here, the minor error which you are given there, correct it and make it 10 to the power positive 3, and the answer is 640. Good. So we are going to discuss AC generators and transformers. On the right side, you have an AC generator. The symbol is what you see, like inverted S here, and this is actually a sinusoidal AC generator. Almost all, I said, unless it's for research purposes, in our homes, the current we get comes from AC generator of this sort. This one you get is a DC generator. Let me show you the picture here. A coil turning in a magnetic field. Okay? There's a change of flux. When there's a change of flux, voltage is induced in the coil. When the ends are connected, I told you current flows. So whether it's this on the right side or the one on the left side, in both cases, the coil is turning and there's a change of flux. But what you have here is commutators and brushes. You get a DC generator. DC means direct current, but the direct current, don't think is like that of a battery on the left side here. It's a pulsating DC. If you connect the ends of the coil to 2 pieces of metal rings, as we discussed last time, the metal rings are called slip rings, and the slip rings move or roll along the surface of 2 pieces of metal that we call brushes here and here. And what you get is an AC. But that's what you find on the right side. So there are two types of AC, and there is one flat DC. AC, meaning a pulsating DC, and alternating current like the one you see from a generator, I mean. Not two types of AC, but two types of current, pulsating DC and an AC like that on the right side. If you want the pulsating DC with, if you remember your grade 10 physics, you can make it something like a flat current of a battery, something like that, approximately, using, you know, there are different resistors and capacitors and so on. So, coil rotates at a constant angular speed. What does experiment show? I hope that sometime in the future we'll meet in some video and I can show you a rotating thing, but not the current. And if you have, for example, a ball rotating in a horizontal circle, and if you shine light on the ball, you tie it with a string and rotate it right around your head at a constant speed, and you follow the shadow of the ball on a wall, the ball moves left and right. And the mathematical formula that gives you the position of the ball is a sine equation. We call it sinusoidal. The same thing is happening here. If you turn a coil in a magnetic field at a constant angular speed, you get a sinusoidal current induced, a sinusoidal voltage as well. If it's sinusoidal, then you write down the voltage is equal to epsilon 0 peak voltage times sine of omega times t. Omega angular speed and t time. Where did that come from? Don't you remember? Grade 10, 11 somewhere, that angular speed is equal to angle divided by time. So if you solve for angle, then you get angular speed times time. All right? Angular speed times time. That's the angle which you find in here. And that angle depends on time. So if these constant, that is like the one given in this picture, if you are turning a coil at a constant speed in a magnetic field, the magnetic field is not changing, the area is not changing. So what is changing? How do you get induced EMF? It's change of flux that induces EMF. And flux means, as you can see here, V times A times cos omega t. Since the changing quantity is only the position of the coil in the magnetic field, neither the magnetic field nor the area of the coil are changing, you can write down then VA delta cos theta over delta t. Theta is omega times t. And omega, as you remember from your grade 11 physics, is 2 pi times frequency. So induced EMF then is equal to minus n times delta phi over delta t NVA omega sine of omega t. All right? What you find here, this delta over delta t, when it is differentiated, let me see over here, what I'm saying is not clear. Induced EMF is equal to N times change of flux over change of time. Let's say changing continuously. So you get B not changing, taken out of the bracket time. A not changing, so you get D over dt of cos theta. Theta is omega times t. So mathematically, when cos is differentiated, it gives you sine. And omega comes out of the term as well. So you get omega times n times b, when this thing differentiated, minus sign, there's a minus sign in front, it gives you a plus. So you get omega times n times b times a times sine of omega t. All right? So that means, as we have assumed in the beginning, that if the induced EMF is sinusoidal, and you write down with the formula epsilon zero, peak voltage times sine omega t, and then comparison of coefficients, sine omega t, gives you the fact that whatever you have here in the derivation in front of the sine term must represent the peak voltage. So peak voltage is equal to N times B times A times omega. Omega is the angular speed with which the coil is being rotated in the magnetic field. So I hope that's not too much for you. It says here, a turbine has an area of 4 meters squared with 2,000 turns rotating in a magnetic field of 40 Tesla. If its frequency is 0.0 hertz, what is the induced EMF in the turbine after 1 second? Well, if you substitute 1 second here in the after 1 second, and you get in front of and B A omega. Where do you put the 1 second? And this sine term. Okay. So B is given, N is given, A is given, and the answer 2 is given there. You try it yourself. Let me see if I have any more. Oh, okay. Let's go through this thing quickly. I still 10 minutes. Let me give you the chance to look at what. Do not forget the formula for peak voltage here. And look at the, before you look at the solution, try it yourself, substitute in here, and try to get the answer. This is only a classwork. It's not even a homework. It's something very simple. I have other important things to discuss with you, and would be at the end of the lesson for today. But this is very, very important for me. The other one problem is so simple. You have the notes with you, and the solution is also given there. Now we come to the basic idea of transformers. We were building up to now to this topic. You see, here on the left side, there is something. What's this something? If you look at the symbol, it's the symbol of an AC generator. DC is of no use if current is not changing, and there will be no more induced voltage. So the current is flowing in 2 different directions. That causes induced EMF, and even when it's flowing in a single current like direction like that of a DC generator, there is a change of current, so there will be an induced EMF continuously. So this generator is connected to one coil drawn in blue. There is a metal passing through the coil, and the metal continues and meets itself here. That means when the current changes, flux is changing. This changing flux passes through the coil, this coil. All right? Flux means a set of magnetic field lines. And magnetic field lines are not open lines. They are closed lines. So each magnetic field line starts from here, goes through this piece of metal, and comes back to its starting point. So you have a closed field. We assume all magnetic field lines approximately pass through this metal. Okay? Since all the magnetic field lines pass through this metal, and when the flux changes, that means there's a change of flux in the coil on the right side. That's the whole point. So when there is a change of flux in the coil on the right side, it induces voltage in itself. I mean, voltage is induced in the coil. Actually, the change, the induction is caused due to the change of magnetic field on the left side. So actually, this is not self-induction, this is mutual induction. What's happening is there, if you connect the ends of this coil, the induced EMF causes induced current, and you can see here above connected, it gives you light. That means there is electric energy, and energy cannot be created or it can't be destroyed. It must come from somewhere. Where did the electric energy come from? It came from the transformer. I mean, it came from the generator on the left side through the process of electromagnetic induction. It can't come. It cannot come from anywhere. Just from nowhere. It can't. So we ask the question. First of all, this thing is mutual induction, and the coil on the left side is called a primary coil. The coil on the left side is called a secondary coil because it's not the one which is causing the whole thing. Voltage is induced in it. It's meant to induce voltage in itself. So this is called the secondary coil. And now, if the bulb glows, we ask one question. How much voltage makes the current to flow through the bulb? This voltage is called secondary voltage. The voltage that we have on the left side, which is connected to the generator, is called the primary voltage. So we want to know the primary voltage, no problem, it comes from the generator. But what about the voltage induced in the second coil, in the secondary coil? How much is it? Well, there is a simple assumption. Like I said in the beginning, if all the magnetic field lines pass through this coil, the second coil I made, there is 100% efficiency. Now we are talking in terms of grade 9 physics, efficiency. If we think that some of the magnetic field lines that pass through the primary coil don't pass through the secondary coil, now there is a wastage of electrical energy. And as an electrical engineer, you try to find a good type of metal. It is called soft iron, and because you wind the coil on it, we call it a core. So after some experimentation, anyway, you come to some device where almost all the flux that appears in the primary flux coil also appears in the second coil. That's it. Now we go over to electromagnetic induction. Induced EMF, is equal to N times rate of change of flux. If you talk about the primary voltage, you get EMF over NP. And here, EMF over N is equal to rate of change of flux. Since we have two coils, if you're talking about the primary, you write down epsilon P over N, NP. If you're talking about the rate of change of flux of the secondary, you write down Vs over Ns. But the rate of change of flux in the primary and the secondary are equal. If they are equal, then epsilon P over epsilon over N for primary and secondary are equal. We do something more now. And instead of writing down epsilon, write down the symbol V, voltage, it doesn't matter. So whether you write down epsilon or V, doesn't make any difference, but in most books, including yours, you find V. So you see, we assume 100% efficiency. The rate of change of flux in the primary without any loss of flux also appears in the secondary, which is not true. It's just like saying, let friction be zero. Friction can never be zero. In the same way, there will be no more current efficiency. So you get this. This is called the first transformer equation. So again, we go over to another equation, to another assumption. You see, we have also power. The power generator, since there is no loss of energy, energy means power times time. You see, in the same time that the energy comes from here to here, the time cancels out. You are transferring power from the primary to the secondary. Thus, if the time is equal, power times time equals power times time. This in the primary, this in the secondary. Time cancels out. So when you assume 100% efficiency, power of the primary is equal to power of the secondary. And power means, as we discussed already, voltage times current. So voltage of primary times current of primary equals voltage of secondary times current of secondary. But we talked about voltage in the previous equation. So if you solve for Vp over Vs, and from here, the first transformer equation, you get Np over Ns, and you bring Np over Ns here and rearrange, you get Np times Ip is equal to Ns times Is, linking current and number of turns. This is called the second transformer equation. Well, we have one problem here. The person sitting on my right side, you know him, seems to tell me that my time is up, I think. And it's just 11:56. I see. Ladies and gentlemen, I'm really sorry. We can solve problems next time. Let me say goodbye to you. Okay? I see only one girl here. I'm saying Iman, and the rest of you, I have to say goodbye to you. Okay? We'll solve problems next time. See ya. Take care of yourself.
Hello students, here we are for another session of electromagnetism. This time there's something very, very interesting. I told you that not 1719, but in 1819, accidentally, Ørsted discovered that current produces a magnetic field. And the reverse process, people asked, is it possible if a current produces a magnetic field, does a magnetic field induce or produce a current? And the answer was yes, and it was discovered. People were purposely looking for this phenomenon, and it was Faraday who discovered it first in 1831. Now we have a proof for that here. Here is a coil, and as I showed you earlier, here is a magnet. I'm going to bring the magnet into the coil. If a magnet moves into a coil, or a magnet moves across a wire, people discovered that voltage will be induced across the ends of the wire. That we call electromagnetic induction. So, you see, this is the North Pole. I'm going to bring it into the coil. Now, the flux of this magnet in the coil is zero. But when I bring it slowly into the coil, the quantity of flux will increase. That means there is a change of flux. Would you please watch over here? Here I have a sensitive ammeter. It's called a galvanometer. So, see please which way the current will be induced when I bring in the magnet. You see, it's induced to the right. When I stop, then this current also stops. When I take it out, magnet is moving away, flux is decreasing, then current will be induced in the opposite direction. Would you please say that again? Here, stop, zero, out, current in the other direction. So this is a sensitive galvanometer. It does two things at the same time. One, it shows the presence of current, and two, it proves also Lenz's law that induced current opposes change of flux. When the North Pole comes in, if current is induced to the right, for example, is flowing this way, let's say, when the magnet is moved out, it will move in the other direction. Due to that, current flows left and right, and therefore such a sensitive device is called a galvanometer. In particular, this sensitive galvanometer has got a zero at the center, therefore it's called center zero galvanometer. May I show that? Remember, rate of change of induced EMF is equal to n times delta phi over delta t. In delta phi, n tells you the number of turns in the coil. Delta phi is B times A times cos theta. So when the magnet is entering cos 0 degree, it would be 1 maximum. But the B delta A over delta T, the flux is changing very quickly. When we change very quickly, we have to have a large induced current. Shall we see that? See? The magnitude of induced current decreases. If I lower it slowly and the change of flux, rate of change of flux is very small, you hardly see any induced current. Watch the galvanometer. You see? You see? The needle is not moving at all. Now I stop. Why? Because the rate of change of flux is slow. Fast change of flux, large quantity of voltage and current induced. Thank you very much. We'll meet in our Zoom next time. Good morning, students. I have a simple demonstration for you. We have about 8 dry cells here, and each one has got a voltage of 1.5, that means approximately 12 volts. With that, I intend to show you the generation of a magnetic field. So, do I have a magnet? Yes. For example, here I have a magnet. How do I know it's a magnet? Because when you suspend it, one end always points towards the North Pole. Another proof for that is that I have also another magnet here. This one too is a magnet. And when we suspend it, this too turns up, turns around in such a way that this is a little bit heavy when it comes to rest, that it points towards north. This one and the marked one are both north poles. So if they are magnets, like poles repel, you must see that. Like poles repel, you can see here, and it attracts the other pole. And another fact is, here I have a ferromagnetic substance. Remember, grade 10 physics, we call it magnetic substance, but it's ferromagnetic now, you're in grade 12. So, it attracts a magnetic substance. But this does not attract other magnetic substances. But so, I'm sure you understand that it's a magnet. Now, does current generate a magnetic field? Here I have 8 dry cells, and the current is passing through a coil, and there is something interesting now. I'll suspend this thing like this. Here, the negative pole is here, the current flows around here, and this is the positive pole. I said the positive pole. So, of the dry cell, the positive terminal. When we connect this one, we have a complete circuit, meaning current is flowing like this. Right hand rule of a coil or a solenoid. When current flows like this, my thumb points towards the North Pole. If this is the North Pole, then it must repel this North Pole, and this end of the magnet must be pulled into it. That's it. Ready? She's going to, when I say connect it, she's going to connect it, and then first, wait. First you can see when it's not connected, nothing happens to the magnet. It's just simply suspended near the coil or the solenoid. But when I say go, she will connect it, and then you will see the change. You see? Release it again, please, Miss Marat. Now you can see there's no magnetic field. The magnet is simply suspended near the coil, and the paper endpoint shows you the North Pole, and when she connects, again, the South Pole will be attracted. That convinces you that, all right? Thank you very much.